Welcome back. Tonight, we settle in with the patient, unhurried work of astronomers who spent long decades peering through brass telescopes at faint smudges of light, cataloging what they called nebulae, those mysterious cloudy patches scattered across the night sky, never quite certain whether they gazed upon distant star clusters, swirling gas, or entire galaxies far beyond our own. A question that would take nearly 2 centuries of careful observation, quiet disagreement, and ever larger mirrors to finally, gently resolve. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. Long before astronomers possessed the instruments or the theoretical frameworks necessary to distinguish between the various types of fuzzy patches scattered across the night sky, careful observers had already begun the slow and patient work of noting their positions and describing their peculiar appearances. And it is to these early chroniclers of the heavens that we now turn our attention, settling into the comfortable rhythm of a story that unfolds across many centuries, each generation adding its own modest contribution to a growing catalogue of celestial mysteries that would not be resolved for hundreds of years yet to come. The ancient skywatchers of Mesopotamia and Egypt certainly noticed the band of soft light we call the Milky Way, that gentle river of luminescence that arches overhead on clear dark nights, and they incorporated this diffuse glow into their mythologies and their understanding of the cosmos. But when it came to individual fuzzy objects beyond this great band, the records become rather sparse, and we must wait until the time of the Greek astronomer Claudius Ptolemy to find systematic attention paid to what he called the nebula stars, those curious points of light that seem somehow softer or hazier than their sharp and brilliant neighbors scattered across the celestial sphere. Ptolemy worked in Alexandria during the 2nd century of the Common Era, around the year 150, compiling and expanding upon centuries of astronomical observations into his great work known as the Almagest, a comprehensive treatise on the movements of the heavens that would remain the authoritative text on astronomy for well over 1,000 years, influencing scholars across the Mediterranean world and beyond. And within this monumental catalogue of over 1,000 stars, Ptolemy made note of several objects that he described as nebulous or cloudy in their appearance, including a fuzzy patch near the star we now call Omicron Velorum and the cluster of stars known as Praesepe in the constellation Cancer, which to the naked eye appears as a soft smudge of light rather than as individual points. And Ptolemy recognized that these objects were somehow different from ordinary stars, though he could not have known why this was so, having no telescope to reveal their true nature and no theoretical framework to explain how such nebulosity might arise. And so he simply recorded what he saw, describing appearances without attempting to explain causes, which was perhaps the wisest approach given the limitations of his time. The centuries following Ptolemy saw relatively little progress in the observation of nebulous objects in European astronomy, as the Western Roman Empire declined and scholarly attention turned elsewhere. But in the Islamic world, where the Greek astronomical tradition was preserved and extended, careful observers continued the work of mapping the heavens, and among the most important of these was the Persian astronomer Abd al-Rahman al-Sufi, who worked in the city of Isfahan during the 10th century and produced his remarkable book of fixed stars in the year 964. A work that updated and corrected Ptolemy's star catalogue based on al-Sufi's own careful observations. And within this beautifully illustrated manuscript, al-Sufi included a description that would prove to be of considerable historical significance, for he noted the presence of what he called a little cloud in the constellation of Andromeda, a faint smudge of light that was visible to the naked eye on clear dark nights. And this little cloud was none other than the great spiral galaxy we now call the Andromeda Galaxy, our nearest large galactic neighbor, lying some 2.5 million light-years distant, though of course Al-Sufi could not have known any of this, perceiving only a subtle patch of luminosity among the fixed stars, unremarkable enough that it had apparently escaped explicit mention in Ptolemy's earlier catalogue, and Al-Sufi's brief notation would stand for many centuries as the earliest known written record of an external galaxy, even though the very concept of a galaxy as a vast island universe of stars would not emerge until nearly 1,000 years later. The invention of the telescope in the early 17th century transformed astronomical observation in ways that the ancient and medieval skywatchers could scarcely have imagined, revealing that the Moon possessed mountains and craters, that Jupiter was attended by 4 bright satellites, that Venus showed phases like our own Moon, and that the Milky Way itself was composed of countless individual stars too faint and too closely packed to be distinguished by the unaided eye. And among the many discoveries enabled by this new instrument was the observation that some of the nebulous patches in the sky resolved into clusters of stars when viewed through even a modest telescope, while others remained stubbornly fuzzy and diffuse no matter how carefully one looked. And this distinction would prove to be of great importance, though its significance would not be fully appreciated for quite some time. In the year 1610, the French astronomer Nicolas Claude Fabry de Peiresc turned his telescope toward the constellation of Orion, that familiar pattern of stars visible from both hemispheres during the winter months of the northern hemisphere. And there, in the region of the Sword of Orion, hanging below the 3 bright stars of the Hunter's Belt, Peiresc observed a patch of luminous nebulosity surrounding a small group of stars, and this observation marked the first telescopic recording of what we now call the Orion Nebula, or Messier 42, one of the most spectacular and well-studied emission nebulae in the entire sky, a vast stellar nursery where new stars are being born even now from collapsing clouds of hydrogen gas and dust, though Peiresc could not have known any of this, perceiving only a mysterious glowing region unlike anything else he had seen. And curiously, this observation seems not to have been widely circulated or remembered, so that later astronomers would rediscover the same object and believe themselves to be the first to have done so. A not uncommon occurrence in the history of astronomy where independent discoveries and rediscoveries frequently complicated questions of priority and credit. The Sicilian astronomer Giovanni Battista Hodiana undertook a more systematic approach to cataloguing nebulous objects, publishing in 1654 a work titled De Admirandis Coeli Characteribus, or On the Wonderful Characters of the Heavens, in which he listed approximately 40 objects that appeared nebulous or hazy when viewed through his telescope, and Hodiana made an interesting attempt to classify these objects into 3 categories, distinguishing between those that were clearly composed of stars, those that appeared partly resolved into stars, and those that remained completely unresolved and nebulous even under magnification, which was a reasonable and practical system given the limitations of his instruments, even if the underlying physical causes of these different appearances remained entirely mysterious. And Hodiana's catalogue represented an early effort to impose some order upon this confused realm of fuzzy celestial objects, though his work was published in Palermo and received relatively little attention from astronomers elsewhere in Europe, so that many of his observations would be independently repeated by later cataloguers who were unaware of his prior work. Just 5 years later, in 1659, the Dutch astronomer and physicist Christiaan Huygens produced a detailed sketch of the Orion Nebula, having independently observed this same object that Peiresc had noted nearly half a century before, and Huygens' drawing captured the distinctive shape of the nebula with considerable accuracy, showing the bright central region and the fainter extensions reaching outward into the surrounding darkness. And he described the nebula as an opening in the sky through which a brighter region beyond was visible. which was an entirely reasonable interpretation given what could be seen through the telescopes of the time, even though we now understand the nebula to be a cloud of glowing gas illuminated by the hot young stars embedded within it, rather than a window to some luminous realm beyond. And Huygens' observation and sketch helped to establish the Orion Nebula as a recognized object of astronomical interest, one that subsequent observers would return to again and again as telescope technology improved and more details could be discerned. The English astronomer Edwin Hubble, best known today for the comet that bears his name, contributed to the growing awareness of nebulous objects with a paper published in the Philosophical Transactions of the Royal Society in 1715, in which he drew attention to 6 luminous spots or patches in the heavens that appeared nebulous even through telescopes. And Halley speculated about the nature of these objects, suggesting that they might be composed of some luminous medium or substance that was fundamentally different from ordinary stars, perhaps representing a primordial material from which stars might form, which was a remarkably prescient intuition even if the details were necessarily vague. And Halley's paper helped to establish nebulae as legitimate objects of astronomical inquiry rather than mere curiosities or observational oddities, worthy of systematic study and theoretical consideration. Throughout this early period, from Ptolemy's nebulous stars to Halley's luminous patches, astronomers faced genuine and profound confusion about what these objects actually were, a confusion that arose not from any failure of intelligence or diligence on their part, but rather from the fundamental limitations of the telescopes available to them. For even the best instruments of the 17th and early 18th centuries could not collect enough light or provide sufficient magnification to reveal the true nature of most nebulous objects. And this meant that several quite different types of celestial phenomena were all grouped together under the same vague heading of nebulae, simply because they all appeared fuzzy and diffuse when viewed through the telescope. Some of these objects were indeed true nebulae in the modern sense, clouds of gas and dust within our own Milky Way galaxy that glow by reflecting starlight or by emitting light of their own when energized by nearby hot stars. And the Orion Nebula that Peiresc and Huygens observed is a splendid example of such a true nebula, a region of active star formation roughly 1,500 light-years from our solar system. Other objects that appeared equally nebulous were in fact globular clusters or open clusters of stars, vast gatherings of hundreds or thousands or even hundreds of thousands of individual suns, so densely packed or so distant that their combined light blurred together into a smooth glow when viewed through small telescopes. And it required larger and more powerful instruments to resolve these clusters into their constituent stars and reveal their true nature as stellar congregations rather than continuous patches of luminosity. And still other objects among the nebulae would eventually prove to be something else entirely, something that the astronomers of this early period could not have conceived, for they were external galaxies, vast island universes containing billions of stars, lying at distances so immense that the individual stars could not possibly be distinguished, and these galaxies appeared as elliptical or spiral smudges of light, easily confused with the various other types of nebulous objects until the 20th century finally brought the theoretical understanding and observational capabilities needed to recognize them for what they truly are. This confusion was not a sign of any deficiency in the early observers, but rather reflected the genuine difficulty of the problem and the inadequacy of the instruments then available. For how could anyone have guessed that some fuzzy patches were clouds of gas a few tens of light years across, while others were collections of stars spanning thousands of light years, and still others were entire galaxies millions of light years distant, when all of them appeared as mere smudges of light in the eyepiece, indistinguishable from one another except perhaps in their brightness or their shape, and when the very concept of a light year had not yet been formulated and the distances to even the nearest stars remained unknown. The astronomers of the 17th and early 18th centuries did the best they could with what they had, cataloguing positions, describing appearances, sketching shapes, and speculating cautiously about causes, building up a body of observations that would prove invaluable to their successors. And if their understanding remained incomplete and their classifications somewhat confused, this was simply the natural state of a science still in its early stages, feeling its way forward through careful observation and tentative hypothesis. And as we consider their efforts from the comfortable distance of several centuries, we might appreciate the patience and dedication they brought to this slow accumulation of knowledge, each observation adding one more small piece to a puzzle whose overall shape was not yet apparent. Each catalogue entry representing hours of careful work at the eyepiece on cold, clear nights, and each published paper contributing to a conversation among scholars that would continue for generations to come, gradually approaching the understanding that now seems so clear to us but which was so hard won by those who came before. Charles Messier was born on the 26th of June in the year 1730, in the town of Badenville, which lies in the Lorraine region of northeastern France, a place of gentle hills and modest industry, where his father worked as an administrative official and where the family of 12 children lived in circumstances that were comfortable enough, though not wealthy by any particular measure. The young Charles was the 10th of these 12 children, and his early years were marked by a notable event in 1744, when he was just 14 years of age, and a great comet with 6 separate tails appeared in the European skies. An apparition so striking and so widely observed that it captured the imagination of the boy and set the course of his entire professional life, though he could not have known this at the time, being simply a young person gazing upward at something beautiful and strange, as so many others were doing across the continent that year. His father passed away when Charles was only 11, and the family's circumstances became more difficult, as often happened in such times when a household lost its primary source of income and stability. The young Messier showed an aptitude for careful, methodical work, and he possessed a neat and precise hand for drafting and recording, skills that would later prove essential to his astronomical career, though in his youth these abilities seemed destined for more ordinary clerical employment. In 1751, when he was 21 years old, he traveled to Paris seeking work, and through some combination of timing and modest good fortune, he secured a position as a clerk and draftsman in the service of Joseph Nicolas Delisle, who was the astronomer of the French Navy and a man of considerable reputation in the scientific circles of the day. Delisle maintained his observatory at the Hôtel de Cluny, a medieval structure in the Latin Quarter of Paris that had once belonged to the abbots of Cluny and which now served as a rather unlikely home for astronomical observation, its rooftop offering views of the Parisian sky that were adequate if not ideal, given the city's growing size and the smoke from countless chimneys that sometimes obscured the fainter celestial objects. Here Messier learned the practical arts of astronomical observation, the patient work of tracking celestial bodies across the sky, recording their positions with careful precision, and maintaining the detailed logs that allowed one observation to be compared meaningfully with another. He learned to use the telescopes and instruments of the observatory. He assisted with the maintenance of records, and he gradually developed the skills that would define his working life for the next 6 decades. The French Navy maintained an interest in astronomy for thoroughly practical reasons, as the determination of longitude at sea remained one of the great technical challenges of the era, and the careful observation of celestial events, including the appearances and movements of comets, contributed to the broader body of knowledge upon which navigational methods depended. Messier's primary duty, which became his consuming passion and the work for which he was officially employed, was the discovery and observation of comets, those wandering visitors to the inner solar system whose appearances were of great interest to astronomers and whose returns, when they were periodic, helped to confirm and refine the gravitational theories that Newton had established in the previous century. Comets, when they first appear in the night sky, often present themselves as small, faint, fuzzy patches of light, distinguishable from stars by their lack of sharp definition, their slightly diffuse appearance, and most importantly by their movement against the background of fixed stars over successive nights of observation. A skilled comet hunter learns to recognize this fuzzy quality, and Messier developed an exceptional eye for detecting these subtle smudges of light that might indicate a new cometary discovery. He would eventually discover or co-discover some 13 comets over the course of his career, a number that was quite substantial for the era, and that earned him recognition from astronomical societies across Europe, including a friendly mention from King Louis XV, who referred to him as the Comet Ferret, a nickname that pleased Messier considerably, as it acknowledged his particular skill and dedication to this specialized form of celestial hunting. However, and this is where our present subject truly begins, Messier encountered a persistent difficulty in his comet searches, a source of frustration that would ultimately lead to his most enduring contribution to astronomy, though he would not have seen it that way himself. The night sky, it turned out, contained numerous objects that were not comets at all but that closely resembled comets to a casual observation through a modest telescope. These objects appeared as faint, fuzzy patches, exactly as a distant comet might appear, and they could easily deceive a comet hunter into believing he had discovered something new and interesting, only for subsequent observations to reveal that the object was not moving, that it remained fixed in its position relative to the surrounding stars, and that it was therefore not a comet at all but rather some permanent feature of the deep sky, a nuisance and a distraction from the real work at hand. These annoying objects were what we would now call nebulae, star clusters, and galaxies, though the distinctions between these categories would not be clearly understood for another century and a half. To Messier, they were simply obstacles, things that got in the way, objects to be identified and catalogued so that he and other comet hunters would not waste their time on them in the future. If he could compile a list of these stationary fuzzy objects and record their positions with sufficient precision, then any comet hunter who spotted a fuzzy patch in one of those recorded positions would know immediately that it was not a comet but merely one of these permanent nuisances, and could continue the search elsewhere without further investigation. The telescopes that Messier used for this work were relatively modest instruments by the standards of the larger observatories of his day, typically reflecting telescopes of about 4 inches in aperture, sometimes slightly smaller, housed on the rooftop of the Hotel de Cluny where the scene conditions were rarely optimal and where the glow of the city's oil lamps added a subtle brightness to the sky that made the detection of faint objects more difficult. Despite these limitations, Messier's patience and systematic approach allowed him to detect and record numerous deep sky objects that had never been formally catalogued before, even though some of them, like the Great Nebula in Andromeda and the nebula in the Sword of Orion, had been observed and noted by earlier astronomers in less systematic fashions. The first object in what would become Messier's famous catalogue was observed on the 12th of September in 1758, when Messier was searching for the expected return of Halley's comet and happened upon a faint, elongated patch of light in the constellation Taurus. This object, which we now call Messier 1 or the Crab Nebula, was clearly not the comet he sought, as it remained stationary on subsequent nights, and it served as an early and prominent example of exactly the kind of deceptive nuisance that Messier wished to document and avoid. The Crab Nebula, we now know, is the remnant of a supernova explosion that was observed by Chinese astronomers in the year 1054, and it represents one of the most studied objects in modern astrophysics, though to Messier it was simply the first entry in a list of things that were not comets. The Great Nebula in Andromeda, which Messier catalogued as his 31st object, had been known to earlier observers, including the Persian astronomer Abd al-Rahman al-Sufi, who described it in the 10th century as a little cloud, and the German astronomer Simon Marius, who observed it telescopically in 1612. But Messier's careful recording of its position and appearance gave it a place in the systematic catalogue that would make it easily identifiable to future observers. We now know that Messier 31 is not a nebula at all but a vast spiral galaxy, containing perhaps 1 trillion stars and lying approximately 2.5 million light-years from our own Milky Way, making it one of the most distant objects visible to the unaided eye on a clear, dark night, though Messier could not have known any of this and would likely have been astonished to learn the true nature of the fuzzy patch he so carefully recorded. Similarly, Messier 42, the Great Nebula in Orion, which hangs in the sword of that prominent winter constellation, was an object that Messier documented with his characteristic precision, noting its position and appearance so that future comet hunters would not mistake it for a wandering visitor. This nebula, unlike the Andromeda object, truly is a cloud of glowing gas, a stellar nursery where new stars are being born from the gravitational collapse of hydrogen and other elements, though again this would not be understood for many generations after Messier's time. In 1774, Messier published his first formal catalogue in the Histoire de l'Académie Royale des Sciences, containing 45 objects that he had determined to be stationary and therefore not comets. The catalogue listed each object by number, gave its position in the sky using the celestial coordinate system of the day, and provided a brief description of its appearance through his modest telescopes, noting whether it was round or elongated, bright or faint, and any other characteristics that might help a future observer to identify it. This publication established the basic format that would be maintained through subsequent editions, and it represented the first systematic attempt to create a comprehensive list of these deep sky objects that might confuse comet hunters. Messier did not work entirely alone in the expansion of his catalogue, and he benefited considerably from his collaboration with Pierre-François-André Méchain, a younger astronomer who had been born in 1744 and who served for a time as Messier's assistant before establishing his own considerable reputation in the field. Méchain was a skilled observer with a particular talent for mathematical calculation, and he contributed numerous objects to the later versions of the Messier catalogue, carefully noting new fuzzy patches and providing their positions to Messier for inclusion in the growing list. The collaboration between these two men was productive and apparently amiable, with Méchain's discoveries being incorporated into the catalogue with appropriate acknowledgement, though the catalogue itself bore only Messier's name and would continue to be associated primarily with him in the centuries that followed. By 1781, the catalogue had grown to 103 objects, representing a substantial survey of the deep sky nuisances that populated the portions of the celestial sphere visible from Paris. The expanded catalogue included star clusters both open and globular, planetary nebulae, diffuse nebulae, and numerous objects that we would now identify as external galaxies, all grouped together without distinction because the physical nature of these various objects remained entirely mysterious, their only common characteristic being that they were fuzzy, they were stationary, and they were not comets. The year 1781 also brought in the tragedy that interrupted Messier's work for an extended period. In November of that year, Messier fell into an ice cellar, a deep pit used for the storage of ice to preserve food, and the fall of some 25 feet left him severely injured with multiple broken bones, including fractures to his arm, leg, and ribs. For a man of 51 years in an era before modern medicine, Such injuries were life-threatening, and Messias' recovery was slow and difficult, keeping him from his observational work for more than a year. He did eventually recover sufficiently to resume his astronomical activities, though some accounts suggest that he never fully regained his former vigor, and his rate of comet discovery slowed in the years that followed. The French Revolution, which began in 1789 and transformed French society through years of upheaval and violence, presented different challenges to Messias' continued work. He had served the old regime. His salary had come from the French Navy and the Royal Astronomical Establishment, and the revolutionary government that replaced the monarchy had little patience for what it might have viewed as aristocratic luxuries. Messier lost his pension during this period, and his financial circumstances became quite difficult, though he managed to survive the most dangerous years of the Terror without suffering the fate of some other members of the old scientific establishment. He continued to observe when he could, maintaining his dedication to the night sky even as the world around him was transformed by political convulsions, and he lived long enough to see his catalogue become a standard reference for astronomical observers, though he likely never imagined that his list of nuisances would eventually become the foundation for amateur astronomy and the study of deep sky objects. Charles Messier died on the 12th of April in 1817, at the age of 86, having devoted more than 60 years to watching the night sky from his rooftop in Paris, recording the comets that passed through and documenting the stationary fuzzy objects that so often deceived him. His catalogue of 103 objects, later expanded by other astronomers to 110 through the inclusion of objects from his notes and correspondence, remains in use today, not as a list of things to avoid, but as a treasured guide to some of the most beautiful and scientifically important objects in the night sky, a gentle irony that Messier himself might have found amusing, though his writings suggest a man of serious disposition who took his comet hunting work very seriously indeed. In the city of Bath, during the middle decades of the 18th century, there lived a musician named Friedrich Wilhelm Herschel, who had come to England from Hanover as a young man and gradually established himself as an organist and composer of some local renown. He was known to his English neighbours as William, and he spent his days teaching music lessons to the children of wealthy families, conducting concerts at the Octagon Chapel, and composing symphonies and concertos that were performed to polite applause in the elegant assembly rooms of that fashionable spa town. His life was comfortable and respectable, filled with the pleasant routines of a provincial music master, and there was little in his circumstances to suggest that he would one day become the most celebrated astronomer of his age, responsible for transforming our understanding of the structure of the heavens and cataloguing thousands of objects that no human eye had ever seen before. The change began gradually, as such transformations often do, with a casual interest that deepened into fascination and eventually into something approaching obsession. Herschel had always possessed a curious and methodical mind, the sort of temperament that finds satisfaction in understanding how things work and in pursuing questions to their logical conclusions. He began reading books on astronomy and natural philosophy, borrowing volumes from lending libraries and purchasing treatises on optics and mathematics, and he found himself increasingly captivated by the idea of examining the heavens for himself, rather than simply reading about what others had observed. The telescopes available for purchase in England at that time were adequate for viewing the moon and the brighter planets, but Herschel quickly realized that if he wished to see fainter and more distant objects, he would need instruments of considerably greater power than anything the London opticians could provide. And so he began to make his own telescopes, teaching himself the difficult art of grinding and polishing metal mirrors in the basement of his house on New King Street in Bath. The work was painstaking and physically demanding, requiring hours of continuous polishing to achieve the precise curvature needed for a good image, and Herschel would sometimes work for 10 or 12 hours without stopping, while his younger sister Caroline read aloud to him or placed morsels of food in his mouth so that he need not interrupt the rhythmic motion of his hands. The mirrors were made from an alloy called specular metal, a mixture of copper and tin that could be polished to a high reflectivity but tarnished quickly and required frequent repolishing. And Herschel experimented endlessly with different proportions and techniques until he had mastered the craft to a degree that surpassed the professional instrument makers of his day. Caroline Lucretia Herschel had followed her brother to England from Hanover, where she had endured an unhappy childhood marked by illness, the lasting effects of smallpox and typhus, and the neglect of a mother who considered her suited for nothing more than domestic service. William had rescued her from this fate, inviting her to Bath to train as a singer and to assist him with his musical endeavors, and she had proven herself a capable soprano who performed regularly in his concerts and oratorios. But as William's attention turned increasingly toward astronomy, Caroline found herself drawn into this new pursuit as well, learning to grind mirrors, to calculate coordinates, and to record observations with the precision and patience that the work demanded. She became not merely her brother's assistant but an astronomer in her own right, and her contribution to the systematic surveying of the heavens would prove indispensable. The method that William Herschel developed for examining the sky was characteristically thorough and systematic, reflecting the same disciplined approach that had made him a successful musician. Rather than directing his telescope toward objects of known interest, as most astronomers did, he resolved to sweep across the entire visible sky in a methodical pattern, examining every region in turn and recording everything he encountered. He would position his telescope at a fixed altitude above the horizon and allow the rotation of the Earth to carry different portions of the sky across his field of view, while Caroline sat nearby at a desk with a clock, a candle, and a notebook, writing down each observation as he called it out and noting the precise time and position. When one strip of sky had been examined, he would adjust the telescope slightly and sweep the next adjacent strip, continuing in this fashion night after night, year after year, building up a comprehensive census of celestial objects that no one had ever attempted before. This approach was laborious and required extraordinary dedication, particularly given the English weather, which offered only intermittent clear nights suitable for observation. Herschel would watch the sky anxiously during the day, and whenever conditions seemed promising, he and Caroline would prepare their equipment and take up their positions as darkness fell, sometimes working until dawn and sleeping only a few hours before William's morning music lessons began. The cold was often severe, and Caroline later recalled nights when the ink froze in her pen and she had to warm it repeatedly over the candle flame, and other nights when the mirror of the telescope became coated with frost and had to be carried indoors to thaw before observations could continue. In March of 1781, during one of these systematic sweeps, William Herschel noticed an object that did not appear quite like an ordinary star, presenting a small but perceptible disk rather than a mere point of light. He initially suspected it might be a comet, which was not an unreasonable assumption given its appearance, and he reported his observation to the Astronomer Royal and other colleagues. But as further observations accumulated and mathematicians attempted to calculate its orbit, it became clear that this was no comet but rather a new planet, the first to be discovered in recorded history, moving in a nearly circular path far beyond the orbit of Saturn. The discovery brought Herschel immediate fame throughout Europe and the patronage of King George III, who granted him an annual pension that allowed him to abandon his musical career entirely and devote himself full-time to astronomy. He moved to the village of Thatchet near Windsor Castle and later to Slough, where he could be near the court and pursue his observations without the distractions of his former profession. Here he constructed ever larger telescopes, culminating in the great 40-foot instrument completed in 1789, a tremendous structure with a mirror nearly 4 feet in diameter supported by an elaborate wooden framework that towered above the garden and required teams of workmen to maneuver into position. The construction of this telescope was an engineering project of considerable ambition, funded by a grant from the king, and it attracted visitors from across Europe who came to marvel at its size and to peer through its eyepiece at the wonders it revealed. The mirror weighed over 1,000 pounds and was cast in a special furnace built on the grounds, a process fraught with difficulty and danger that required multiple attempts before a satisfactory result was achieved. Yet despite its fame, the 40-foot telescope proved somewhat unwieldy for regular observations, and Herschel found that much of his most productive work was accomplished with smaller instruments that could be more easily handled and more quickly directed toward different parts of the sky. The systematic sweeping continued unabated, and the observations accumulated in Caroline's neat handwriting, filling volume after volume with descriptions of nebulae, star clusters, double stars, and other curious objects that had never been recorded before. The results of these surveys were published in 3 major catalogues, appearing in the Philosophical Transactions of the Royal Society in 1786, 1789, and 1802. The first catalogue contained 1,000 nebulae and star clusters, the second added another 1,000, and the third contributed 500 more, bringing the total to approximately 2,500 objects, an enormous increase over the 100 or so nebulae that had been known before Herschel began his work. Each entry included a description of the object's appearance, its approximate position in the sky, and often Herschel's speculations about its nature and structure, whether it appeared round or elongated, bright or faint, resolvable into stars or remaining stubbornly hazy even at the highest magnifications his instruments could provide. The theoretical implications of these observations occupied Herschel's mind throughout this period, and in 1785 he presented a paper to the Royal Society entitled On the Construction of the Heavens, in which he proposed a bold and far-reaching model of the universe based on his survey data. He suggested that the Milky Way was a vast stratum of stars arranged in a flattened disk, with our solar system located somewhere within this disk, and that many of the nebulae he had observed were similar systems lying at immense distances beyond our own, separate island universes scattered through the depths of space. This was a visionary conception, anticipating by more than a century the modern understanding of galaxies, and it represented a dramatic expansion of the scale on which the universe was imagined. However, Herschel was too careful an observer to cling to a theory when the evidence began to suggest otherwise, and his views evolved considerably as his surveys progressed and as he encountered objects that did not fit comfortably within his initial framework. The planetary nebulae proved particularly troublesome, appearing as small, round, greenish disks that resembled planets in shape but clearly were not, and that seemed to possess a genuinely gaseous or luminous quality quite different from the aggregations of stars he had expected to find. By the later years of his career, Herschel had largely abandoned the island universe hypothesis in favor of the view that at least some nebulae were composed of a diffuse luminous fluid, perhaps a primordial material from which stars might eventually condense, a position that aligned more closely with the nebula hypothesis that was gaining currency among natural philosophers of his time. Throughout these decades of work, Caroline Herschel maintained her own observing program in addition to her duties as recorder and assistant, and she achieved considerable distinction in her own right. Using a small telescope that William had made for her, She discovered 8 comets between 1786 and 1797, several of which still bear her name, and she compiled catalogues and indices that organized and made accessible the vast body of observations that she and her brother had accumulated. Her contributions were recognized by the Royal Astronomical Society, which awarded her its gold medal in 1828, making her the first woman to receive this honor, and later granted her honorary membership, a distinction shared at that time by only one other woman. The work begun by William and Caroline Herschel did not end with their passing but was continued and extended by the next generation. John Herschel, William's only son, inherited his father's passion for astronomy and his methodical temperament, and he devoted himself to completing and expanding the survey of the heavens that his father had begun. Having swept the skies visible from England, John resolved to extend the census to the southern hemisphere, which contained many regions that could never be seen from European latitudes, and in 1834 he transported his family and his telescopes to the Cape of Good Hope at the southern tip of Africa, where he established an observatory and spent 4 years systematically examining the unfamiliar constellations of the southern sky. The observations made during this expedition added thousands of new objects to the catalogues, including nebulae and star clusters in the Magellanic Clouds, those 2 hazy patches of light visible only from southern latitudes that would later prove to be neighboring galaxies. John Herschel's General Catalogue of Nebulae and Clusters, published in 1864, combined his own observations with those of his father and aunt and other astronomers into a comprehensive listing of over 5,000 objects, a monument to 3 generations of patient work and a foundation upon which all subsequent catalogues would build. The sweeping of the heavens by the Herschel family thus represents one of the great sustained efforts in the history of observational science, a systematic and disciplined program pursued across decades and continents that revealed the true richness and complexity of the universe beyond our solar system. The objects they discovered and catalogued, numbered and described in their careful records, would occupy astronomers for generations to come, each nebula and cluster a puzzle waiting to be solved, a distant system waiting to be understood, a faint smudge of light holding secrets that patience and ingenuity would eventually unlock. In the gentle rolling countryside of Central Ireland, in the county of Offaly, there stands an estate known as Birr Castle, and it was here, in the middle decades of the 19th century, that one of the most remarkable astronomical instruments ever constructed came into being, a telescope of such extraordinary dimensions that it would remain the largest in the world for more than 7 decades, and its creator, William Parsons, the 3rd Earl of Ross, would use this magnificent device to peer deeper into the mysteries of the nebulae than any observer before him, revealing structures and forms that would reshape how astronomers thought about these distant cloudy patches of light, though many years would pass before the true significance of his discoveries could be fully appreciated. William Parsons was born in the year 1800 into a family of considerable wealth and social standing, and from an early age he displayed a keen interest in matters of science and engineering, attending Trinity College Dublin and later Magdalen College Oxford, where he studied mathematics and developed the practical skills that would serve him so well in the years to come. Unlike many aristocrats of his era who might have contented themselves with the leisurely pursuits befitting their station, Parsons devoted himself with quiet determination to the advancement of astronomical knowledge, and he understood that to see further into the depths of space, one required instruments of ever greater power, which meant mirrors of ever larger diameter, and so he set about the patient work of learning how to cast and polish the great specular metal mirrors that formed the heart of reflecting telescopes of that age. Specular metal, for those who may not be familiar with this material, was an alloy consisting primarily of copper and tin, mixed in careful proportions to produce a surface that could be ground and polished to a high reflectivity, though this metal was notoriously difficult to work with, being brittle and prone to tarnishing when exposed to the damp air. And the larger the mirror, the greater the challenges became, for the casting process required precise control of temperature and cooling rates to prevent the formation of cracks or bubbles that would ruin the optical surface. Parsons experimented for many years, building progressively larger telescopes at Birk Castle, learning from each attempt the subtle techniques required to produce mirrors of acceptable quality. And by the late 1830s he had constructed a telescope with a mirror measuring 36 inches in diameter, which was itself a significant achievement. But his ambitions extended further still, toward a mirror that would measure a full 6 feet, or 72 inches, across its gleaming surface. The construction of this great mirror occupied several years of painstaking effort, with Parsons employing workers from the local estate and training them in the specialized skills required for such delicate work, for there were no established manufacturers capable of producing optical components of this unprecedented scale. The mirror blank was cast in a furnace built on the castle grounds, and the cooling process alone required many weeks, as the massive disk of metal had to release its heat gradually to avoid the internal stresses that would otherwise shatter it into useless fragments. The finished mirror weighed nearly 4 tons, and its surface had to be ground and polished to a precise curvature using techniques that Parsons had developed through years of careful experimentation. And the entire process represented a triumph of practical engineering as much as theoretical understanding, a testament to the methodical patience that characterized all of the Earl's scientific work. The mounting of this enormous mirror presented challenges every bit as formidable as its construction, for the instrument had to be capable of tracking celestial objects as they moved across the sky due to the rotation of the Earth. Yet the weight of the mirror and its supporting tube was so great that conventional mounting designs would have been wholly inadequate. Parsons solved this problem through a design of elegant simplicity, constructing 2 massive walls of masonry, each standing some 50 feet in height and running roughly north to south, between which the great tube of the telescope was suspended by chains and counterweights that allowed it to swing through an arc tracing the meridian, the line running from due north to due south through the highest point of the sky. This arrangement meant that the telescope could observe objects only as they crossed the meridian, which limited somewhat the range of objects that could be studied. But within these constraints, the instrument possessed extraordinary power, gathering light from sources so faint that no previous telescope had been capable of revealing them. The telescope was completed in the year 1845, and it quickly became known as the Leviathan of Parsonstown, a name that captured something of the awe it inspired in all who beheld it, for there was nothing else in the world quite like this great machine standing between its stone walls in the Irish Midlands, pointing upward toward the heavens with its 6-foot eye of polished metal. Visitors came from across Europe and beyond to marvel at this creation, and astronomers recognized immediately that Parsons had provided the scientific community with an instrument capable of revealing details in the nebulae that had remained hidden from all previous observers, details that might help to resolve the lingering questions about the true nature of these mysterious objects. Among the first targets that Parsons examined with his new telescope was a nebula catalogued by Charles Messier as M51, located in the constellation of Canes Venatici, which previous observers had noted as an interesting double system consisting of a larger fuzzy patch connected to a smaller companion. What Parsons saw through the eyepiece of the Leviathan was something altogether unexpected, for the larger component displayed a distinct spiral structure, with curved arms winding outward from a bright central region, a form that had never before been observed in any celestial object. He made careful drawings of what he saw, recording the delicate tracery of these spiral arms with the skill of a trained draftsman, And when these drawings were published in the Philosophical Transactions of the Royal Society, they caused considerable excitement among astronomers, for here was evidence that at least some nebulae possessed organized structures of remarkable complexity, structures that seemed difficult to explain if these objects were merely clouds of glowing gas or collections of unresolved stars scattered randomly through space. The drawings that Parsons produced deserve particular mention, for in an age before astronomical photography had developed to the point of being useful for recording faint objects, the skilled observer with pencil and paper remained the primary means of preserving what the telescope revealed. Parsons possessed genuine artistic ability, and his renderings of M51 and other nebulae combined scientific accuracy with a delicate aesthetic sensibility, capturing not only the positions and brightnesses of features, but also something of their subtle textures and gradations. These drawings were reproduced through the printing process and distributed to astronomers around the world, allowing those who could never hope to look through the Leviathan themselves to share in the discoveries it made possible, and they remained the standard reference for the appearance of many nebulae for decades afterward. The Leviathan revealed spiral structure in numerous other nebulae as well, establishing that M51 was not a unique curiosity but rather a representative of what appeared to be a distinct class of objects, and Parsons compiled an extensive catalogue of these spiral nebulae over the years that followed, adding to our knowledge of the variety of forms that these distant objects could take. Yet for all the power of his instrument, Parsons was never able to resolve the spiral nebulae into individual stars, which left open the fundamental question of whether they were truly remote systems comparable to our own Milky Way, as Thomas Wright and Immanuel Kant had speculated a century earlier, or whether they might be nearby formations of gas and dust illuminated by embedded stars or some other mechanism. The island universe hypothesis, as this idea came to be known, would remain a topic of active debate for many decades after Parsons had made his observations, and while his work provided crucial evidence that would eventually support this theory, he himself remained cautious about drawing conclusions that went beyond what his observations could definitively establish. The Irish weather proved to be a persistent obstacle to the work at Birk Castle, for the climate of the Midlands is characterized by frequent cloud cover and atmospheric instability, conditions that are far from ideal for astronomical observation, which requires clear skies and steady air to reveal fine details in distant objects. Parsons and his assistants often found themselves waiting for weeks between nights suitable for observation, and even on those occasions when the skies cleared, the seeing conditions were frequently mediocre at best, limiting the effective resolution of the great telescope. This was a source of considerable frustration, for the instrument possessed the theoretical capability to reveal details finer than could typically be observed, and one can only imagine what additional discoveries might have been made if the Leviathan had been situated beneath the clear skies of a mountaintop in a more favorable climate. Despite these limitations, the work continued with patient determination, and Parsons was assisted in his observations by several individuals who would themselves go on to distinguished careers in science. George Johnston Stoney served as an astronomical assistant at Birk Castle in the 1850s before becoming a professor at Queen's College, Galway, where he would later introduce the term electron for the fundamental unit of electrical charge. Robert Stowell Ball also worked at Birr during the 1860s, serving as director of the observatory, and he would subsequently become Astronomer Royal of Ireland and a popular lecturer on astronomical subjects, bringing knowledge of the heavens to audiences throughout Britain and Ireland. These assistants contributed to the observing program and helped to maintain the great telescope in working order, for an instrument of such complexity required constant attention, and the specular metal mirrors in particular needed regular repolishing to maintain their reflectivity. One ought also to mention Lady Mary Ross, who was herself a woman of considerable scientific accomplishment, for she took up the practice of photography at an early date, mastering the difficult wet collodion process and producing images of considerable technical quality. Her photographs documented the great telescope and the work at Birk Castle, providing a visual record of this remarkable enterprise, and she received recognition for her accomplishments from the Dublin Photographic Society and other organizations. In an era when women were largely excluded from formal scientific institutions, Lady Rosse found ways to contribute meaningfully to the intellectual life of the estate, and her work deserves to be remembered alongside that of her husband. Among the other objects that Parsons examined with the Leviathan was the nebula catalogued as M1, located in the constellation of Taurus near the star marking the tip of one of the bull's horns. This object had been known since the early 18th century, having been discovered by the English physician and amateur astronomer John Bevis in 1731, and Messier himself had observed it while searching for comets, including it as the first entry in his famous catalogue to prevent future confusion. Previous observers had noted that M1 presented a somewhat elongated appearance, but Parsons was able to discern considerably more detail, observing that the nebula possessed a complex filamentary structure with delicate strands and wisps extending through its interior. He noted that the overall shape of the nebula reminded him somewhat of a crab, and while this comparison may not strike every observer as particularly apt, the name Crab Nebula has persisted to the present day, becoming one of the most familiar designations in all of astronomy. The observations of the Crab Nebula would prove to have particular significance in later years, for this object would eventually be identified as the remnant of a supernova explosion that was recorded by Chinese astronomers in the year 1054, and it would become one of the most intensively studied objects in the sky, yielding discoveries about pulsars, synchrotron radiation, and the processes by which massive stars end their lives. But in the 1840s, none of this could be known, and Parsons simply recorded what he saw, adding another piece to the slowly assembling puzzle of nebular astronomy. William Parsons continued his observations until his health began to decline in the 1860s, and he passed away in the year 1867, leaving behind a legacy that would influence astronomical research for generations to come. The great telescope remained in use for some years afterward under the direction of his son, the fourth Earl, but as newer instruments were constructed at more favorable sites around the world, the Leviathan gradually fell into disuse, and by the early 20th century it had become more of a historical curiosity than an active research tool. Yet the observations made during its years of operation had established beyond doubt that the nebulae encompassed objects of remarkable diversity, some showing the spiral forms that would eventually be recognized as external galaxies, others displaying the filamentary structures of supernova remnants, and still others appearing as the glowing shells of gas surrounding dying stars. The full resolution of these distinctions would require many more decades of work, but the foundations had been laid in the quiet parkland of an Irish country estate, where a patient and methodical aristocrat had built the largest telescope the world had ever seen and pointed it toward the distant mysteries of the night sky. And so we come now to a quieter kind of discovery, one made not by peering deeper into the darkness or building ever larger telescopes, but rather by learning to read the light itself, to understand what the gentle glow from those distant fuzzy patches was actually trying to tell us, if only we could learn its language. This chapter of the story unfolds in the most unlikely of settings, not at a great national observatory or a university research station, but in the back garden of a terraced house in South London, where a wine merchant's son and his remarkably talented wife would together unlock secrets that had puzzled astronomers for more than a century. Before we arrive at that garden in Tulse Hill, though, We must first go back a few decades to understand the tools that made such discoveries possible, and for this we turn to Bavaria in the early 19th century, where a young man named Joseph von Fraunhofer was working in the optical trade, grinding and polishing lenses with extraordinary precision. Fraunhofer was something of a tragic figure in many ways. Orphaned young, nearly killed when the workshop where he was apprenticed collapsed upon him, yet rescued and subsequently supported by patrons who recognized his unusual gifts. He became, in time, the finest maker of optical glass in all of Europe, and it was through this work that he made an observation which would prove fundamental to everything that followed. In the year 1814, Fraunhofer was testing the quality of his prisms by passing sunlight through them, spreading the light out into its constituent colors as Newton had done more than a century before, that familiar rainbow band running from deep red through orange and yellow and green to blue and violet at the far end. But Fraunhofer noticed something that Newton had not recorded, or had perhaps not examined closely enough to see. The spectrum of sunlight was not a smooth continuous band of color at all, but was instead crossed by hundreds of fine dark lines, thin gaps where certain precise wavelengths of light appeared to be missing entirely. He mapped these lines with meticulous care, identifying the most prominent ones with letters of the alphabet, and though he did not fully understand what caused them, he had given future scientists a tool of immense power. For those dark lines, which we now call Fraunhofer lines in his honor, would prove to be a kind of fingerprint, a way of identifying the chemical elements present in a light source even when that source was impossibly far away. The explanation for these dark lines came gradually, through the work of several scientists over the following decades. It was understood eventually that each chemical element, when heated to incandescence, produces light at very specific wavelengths, creating bright lines at particular positions in the spectrum, and that the same element, when cooler gas lies between the light source and the observer, will absorb light at exactly those same wavelengths, creating dark lines instead. The spectrum of sunlight showed dark lines because cooler gases in the outer atmosphere of the Sun were absorbing particular wavelengths from the hotter continuous glow beneath. This meant that by analyzing the pattern of lines in any source of light, one could in principle determine what elements were present, a kind of chemical analysis performed across vast distances using nothing but light itself. It was this technique, which we call spectroscopy, that William Huggins began to apply to the stars and nebulae from his private observatory in the London suburb of Tulse Hill, beginning in the year 1856. Huggins was not a professional astronomer but rather a gentleman scientist of independent means, having sold the family silk and linen business to devote himself entirely to the study of the heavens. He built himself a well-equipped observatory in the garden of his home, furnished it with a fine 8-inch refracting telescope, and set about the patient work of attaching spectroscopic apparatus to this instrument so that he might examine the light of celestial objects in this new and revealing way. He was not working alone in this endeavor, though the contributions of his collaborator would for many years go largely unacknowledged in the scientific literature of the time, as was unfortunately common when that collaborator happened to be a woman. Margaret Lindsay Murray, who became Margaret Huggins upon her marriage to William in 1875, was herself a skilled astronomer and spectroscopist, and the two of them formed a remarkable scientific partnership that would span decades. Margaret had been fascinated by astronomy since childhood, had built her own spectroscope, and brought to the collaboration not only technical skill but also a talent for the precise and delicate work of recording spectroscopic observations. Together they would produce work of lasting importance, though William's name alone typically appeared on the resulting publications. a convention of the era that Margaret herself seems to have accepted with equanimity, focused as she was on the work itself rather than on recognition. The observation that would prove most consequential came on the night of the 29th of August in the year 1864, when William Huggins turned his spectroscope toward a planetary nebula in the constellation Draco, the object we now catalogue as NGC 6543, though it is more commonly known as the Cat's Eye Nebula for its distinctive appearance in modern photographs. What Huggins saw through his spectroscope that night was something entirely unexpected, something that would settle at last the long-standing question of whether nebulae were clouds of gas and dust or merely distant collections of stars too faint and numerous to be resolved individually. When Huggins had previously examined the light of stars through his spectroscope, he had seen what one would expect from a hot glowing solid or dense gas, a continuous rainbow spectrum crossed by dark absorption lines, the pattern of colors and lines varying somewhat from star to star but always showing that characteristic continuous band. The nebulae, if they were indeed distant star systems as many astronomers believed, should have shown something similar, a blended version of many stellar spectra overlapping to produce a continuous glow. But the planetary nebula NGC 6543 showed nothing of the kind. Instead of a continuous spectrum, Huggins saw only a few isolated bright lines, points of light at specific wavelengths against an otherwise dark background. This was the signature not of a solid body or a dense collection of stars, but of a thin hot gas, glowing by emission rather than by the reflection or transmission of light from some other source. The implications were immediately clear to Huggins, and he would later write of the excitement of that moment, though for our purposes we may simply note that he had proven what William Herschel had long suspected, that at least some of the nebulae were indeed vast clouds of luminous gas rather than unresolved star systems. The spectrum told the story plainly, for no collection of stars, however distant, would produce light only at a few isolated wavelengths while leaving the rest of the spectrum dark. This was gas, glowing in the depths of space, and the bright lines in its spectrum could in principle identify exactly what kind of gas it was. Huggins quickly identified two of the bright lines as belonging to hydrogen, matching wavelengths that were already known from laboratory experiments on Earth. But there was a third line, a bright green line that did not match any element known to terrestrial chemistry, falling at a wavelength of approximately 5007 angstroms, with a fainter companion line nearby at 4959 angstroms. This mysterious green glow was soon found in other nebulae as well, and it was given the provisional name nebulium, as though it were a new element found only in these cosmic gas clouds and nowhere else in the universe. The mystery of nebulium would persist for more than 60 years, and we shall return to its eventual solution in a few moments. But first we should note a related discovery made just 4 years after Huggins examined the Cat's Eye Nebula, a discovery that seemed at first to suggest that strange elements unknown on Earth might indeed exist in celestial objects. In 1868, the English astronomer Joseph Norman Lockyer was observing the spectrum of the Sun during a solar eclipse, examining the bright prominences that rise from the solar surface and become visible when the main disk is blocked by the Moon. In this spectrum he found a bright yellow line that did not match any known element, falling very close to but not precisely at the wavelength of the well-known sodium lines. Lockyer proposed that this indicated a new element, and together with the chemist Edwin Hubble, he gave it the name helium, from the Greek word helios meaning sun. Unlike nebulium, helium turned out to be quite real, eventually being discovered on Earth in 1895 when William Ramsay isolated it from a uranium mineral. But the precedent was set, and it was not unreasonable for astronomers to suppose that Nebulium too might be a genuine element awaiting discovery. The periodic table still had gaps in those days, and the universe seemed a large enough place to contain elements not yet found in terrestrial laboratories. Returning to William and Margaret Huggins, we find them continuing their spectroscopic work through the following decades, refining their techniques and extending their observations to ever fainter objects. In 1868, William attempted something particularly ambitious, an effort to measure the Doppler shift of spectral lines in the star Sirius, which would allow him to determine whether the star was moving toward or away from the Earth. The Doppler effect, named for the Austrian physicist Christian Doppler, who had described it theoretically in 1842, predicts that light from a source moving toward the observer will be shifted slightly toward shorter wavelengths, appearing more blue, while light from a receding source will shift toward longer wavelengths, appearing more red. By measuring how far the spectral lines of a star had shifted from their expected laboratory positions, one could in principle calculate the star's velocity along the line of sight. Huggins' 1868 observations of Sirius suggested that the star was indeed receding from Earth at a measurable velocity, though his early measurements were not particularly accurate by modern standards, the technique being fiendishly difficult and requiring equipment pushed to its very limits. Nevertheless, he had demonstrated the feasibility of the method, which would become one of the most important tools in all of astronomy, eventually enabling the measurement of cosmic distances and the discovery of the expanding universe itself, though those developments lay many decades in the future. The spectroscopic observations of nebulae led naturally to a classification scheme based on the type of spectrum each object displayed. Those nebulae showing bright emission lines, like the Cat's Eye Nebula, were understood to be clouds of glowing gas, their light generated by the gas itself rather than by embedded stars. But other nebulae, including many of the spiral forms that Lord Rosse had so carefully drawn, showed continuous spectra more like those of stars, sometimes crossed by absorption lines. These came to be called white nebulae in some classification schemes, and their true nature remained uncertain. Were they clouds of gas illuminated by embedded stars, or were they something else entirely, perhaps those island universes of stars that some astronomers had proposed? The spectroscopic evidence alone could not settle this question, for a distant collection of countless stars would produce a blended spectrum rather similar to that of a gas cloud reflecting stellar light, and distinguishing between these possibilities would require other methods. We have mentioned that the mystery of Nebulium persisted for many decades, with that bright green line appearing in nebula after nebula, always at the same wavelengths, 5,007 angstroms and 4,959 angstroms, yet matching no element that chemists could identify in their laboratories. The solution finally came in 1927, when the American physicist Ira Sprague Bowen, working at the California Institute of Technology, realized that Nebulium was not a new element at all, but was in fact ordinary oxygen, glowing in a way that could never be reproduced in a laboratory on Earth. Bowen's explanation relied on the concept of forbidden transitions, quantum mechanical processes that are not truly forbidden but merely extremely improbable, so unlikely to occur that they effectively never happen under normal laboratory conditions. In a laboratory, atoms of oxygen collide with one another and with container walls billions of times per second, and any energy an atom gains is quickly shared with its neighbors through these collisions before the atom has a chance to emit light through a forbidden transition. But in the thin gas of a nebula, where atoms may drift for hours or even days between collisions, there is time for even the most improbable processes to occur. The oxygen atoms in nebulae can slowly release energy through these forbidden transitions, emitting photons at those characteristic green wavelengths that had puzzled astronomers for more than 60 years. This explanation was deeply satisfying, for it required no new element, no exotic cosmic chemistry, but rather showed that the familiar element oxygen would behave in unfamiliar ways when placed in conditions that could never be achieved on Earth, the near-perfect vacuum and isolation of interstellar space. The green glow of the nebulae was oxygen, doubly ionized oxygen to be precise, oxygen atoms that had lost 2 of their electrons and were radiating away energy in the only way available to them under those extraordinary conditions. And so by the late 1920s, the tools of spectroscopy had revealed much about the nature of nebulae, showing that at least some of them were indeed clouds of gas, composed of hydrogen and oxygen and other familiar elements, glowing in the darkness between the stars. The gaseous nebulae could now be understood as separate from the white nebulae with their stellar spectra, though the true nature of those white nebulae, those spiral forms that seem to suggest island universes of distant stars, would require still further investigation before the matter could be settled. But for now, for this quiet moment, we may rest with the knowledge that light itself had been made to speak, that the patient work of William and Margaret Huggins in their garden observatory had opened a new window on the cosmos, allowing us to know not just where things were in the sky, but what they were made of, reaching across the impossible distances to perform a kind of chemistry on clouds of gas so diffuse that a single breath would contain more matter than 1,000 cubic miles of nebula, clouds that glow with the patient light of forbidden transitions, green and soft in the darkness, taking their time, always taking their time. For much of the history of astronomy, the human eye remained the only instrument capable of receiving the faint light that traveled across the vastness of space, and while telescopes could gather and magnify that light, the astronomer still had to peer through the eyepiece and attempt to perceive whatever details the universe might offer in that fleeting moment of observation. The eye, remarkable as it is, has certain limitations that proved particularly troublesome when studying nebulae, those dim and diffuse objects that seem to hover at the very edge of visibility. The eye cannot accumulate light over time, and so a faint object appears no brighter after 5 minutes of staring than it did in the first instant of observation. The eye also struggles to perceive subtle gradations of brightness across extended objects, and the memory of what one has seen can shift and change even as one attempts to commit it to paper. These limitations meant that our understanding of nebulae remained somewhat uncertain, dependent on the skill and visual acuity of individual observers, and subject to the kinds of disagreements that arise when different people describe slightly different impressions of the same phenomenon. The development of photography offered a solution to many of these difficulties, though the early photographic processes were themselves quite limited in their sensitivity to light, and it took several decades of patient experimentation before astronomers could successfully apply this new technology to the challenge of recording nebulae. The daguerreotype process, introduced in 1839, allowed for the capture of the moon and eventually the sun, and later the wet collodion process permitted images of bright stars to be recorded. But nebulae presented a far greater challenge because their light is spread across a considerable area of the sky rather than concentrated in a single brilliant point. To photograph a nebula, one needed not only a sensitive photographic plate but also a telescope capable of following the apparent motion of the stars with great precision over an extended period, allowing the faint light to accumulate gradually on the emulsion until an image emerged from the darkness. On the evening of the 30th of September in 1880, a physician and amateur astronomer named Henry Draper succeeded in obtaining what is generally recognized as the first successful photograph of a nebula, capturing the Great Nebula in the constellation of Orion from his private observatory in Hastings-on-Hudson, a pleasant village along the river north of New York City. Draper had constructed his observatory with considerable care and had devoted many years to the refinement of his instruments and techniques, grinding his own telescope mirrors and developing methods for driving his telescope to compensate for the rotation of the Earth. On that September night, he exposed his photographic plate for 51 minutes, guiding the telescope by hand throughout the exposure to ensure that the faint light of the nebula would fall consistently on the same portion of the sensitive emulsion. The resulting image was modest by later standards, showing only the brightest central regions of the nebula, but it represented a profound achievement nonetheless, demonstrating that the camera could record what the eye could see and suggesting that it might eventually reveal far more. Draper continued his photographic work in the months that followed, obtaining additional images of the Orion Nebula with exposures of varying duration, and he also succeeded in photographing the spectrum of this nebula, confirming through an entirely independent method that it consisted of luminous gas rather than unresolved stars. Sadly, Draper did not live to see the full flowering of the photographic revolution he had helped to initiate, as he died unexpectedly in 1882 at the age of 45. But his work had demonstrated the essential feasibility of nebula photography and had inspired others to pursue this line of investigation with improved instruments and techniques. Among those who took up the challenge was Andrew Ainslie Common, an English amateur astronomer who had constructed a reflecting telescope with a mirror of 36 inches in diameter, considerably larger than the instruments available to most professional observatories of that era. Common devoted himself to the technical challenges of long-exposure photography, developing improved clock drives and guiding mechanisms that allowed him to track celestial objects with remarkable precision over extended periods. In January of 1883, Common obtained a series of photographs of the Orion Nebula that marked a significant advance over Draper's pioneering images, not merely in their clarity and detail but in something far more consequential. When Common examined his photographic plates, he discovered that they revealed stars within and around the nebula that no human eye had ever perceived. Stars too faint to be seen even through the most powerful telescopes when observed visually, but present nonetheless on the sensitive emulsion that had patiently accumulated their light over the course of the exposure. This discovery carried profound implications for the future of astronomy, suggesting that photography was not merely a convenient method for recording what visual observers had already seen, but rather a means of extending human perception into realms that had previously been entirely inaccessible. The photographic plate, with its capacity to accumulate light over minutes or even hours, could effectively create a larger eye than any biological organism could possess, gathering photons from distant and feeble sources until their collective effect became sufficient to leave a permanent record. Common's photographs of the Orion Nebula earned him the gold medal of the Royal Astronomical Society in 1884, one of the highest honors in the field, awarded in recognition of his demonstration that photography could reveal celestial objects and details invisible to direct visual observation. The spiral structure of certain nebulae, which Lord Rosse had glimpsed through his great telescope at Birk Castle, found new confirmation and clearer expression through the photographic work of Isaac Roberts, a Welsh amateur astronomer who had established an observatory near Crowborough in the Sussex countryside. Roberts had made a fortune in the construction trade and had devoted his later years to the pursuit of astronomical photography with a dedication and patience that yielded remarkable results. In December of 1888, Roberts obtained a photograph of the Great Nebula in Andromeda, known also by its catalogue designation as Messier 31, that revealed its structure with unprecedented clarity. The image showed not a fuzzy patch of light but a vast oval form with a bright central condensation, surrounded by what appeared to be spiral arms winding outward from the core, along with dark lanes that seemed to represent regions where light was somehow obscured or absent. Roberts interpreted this image as showing a solar system in the process of formation, with the central condensation representing a nascent sun and the spiral structure representing the material from which planets might eventually coalesce, an interpretation that fit well with the nebula hypothesis of Laplace but which would eventually prove incorrect in ways that Roberts could not have anticipated. Regardless of the accuracy of his interpretation, Roberts' photograph of the Andromeda Nebula demonstrated that photography could capture the large-scale structure of these objects in ways that visual observation and hand-drawn sketches could not easily match, providing a permanent and objective record that could be studied and measured long after the original observation had concluded. During this same period, an ambitious international project was initiated that would apply photographic methods to the systematic mapping of the entire sky. The Carte du Ciel project, proposed by the director of the Paris Observatory and formally organized at an international congress in 1887, sought to create a comprehensive photographic atlas of the heavens using standardized instruments and techniques deployed at observatories around the world. 18 observatories ultimately participated in this enormous undertaking, each assigned a specific zone of the sky to photograph and catalogue, with the goal of recording every star down to a certain threshold of brightness and producing both a photographic atlas and a catalogue of stellar positions. The project proved far more difficult and time-consuming than its originators had anticipated, and it was never fully completed according to its original design, but it nonetheless represented an important step in the transformation of astronomy from a discipline dependent on individual visual observations to one based on systematic photographic surveys, establishing methods and standards that would influence astronomical practice for decades to come. The application of photography to the discovery of dark nebulae, those mysterious regions where the stars seem to be absent, was advanced significantly through the work of Edward Emerson Barnard, an American astronomer whose visual acuity and dedication to observation were matched by his skill with photographic instruments. Working at Lick Observatory in California, with its clear mountain skies and excellent seeing conditions, Barnard employed wide-field cameras capable of recording large swaths of the Milky Way in a single exposure. His photographs revealed that the dark patches and lanes visible in the Milky Way were not simply regions devoid of stars, but rather appeared to be clouds of some obscuring material that blocked the light of more distant stars behind them. The shapes and edges of these dark regions were too well defined to be explained by mere statistical variations in stellar density, and Barnard's photographs provided compelling evidence that space was not entirely transparent, that there existed vast clouds of dark matter, matter in the original sense of material substance rather than the modern cosmological usage, that could absorb or scatter the light passing through them. Barnard devoted many years to the photography and cataloguing of these dark nebulae, eventually publishing an atlas that documented their positions and forms across the Milky Way, and his work helped to establish the existence of what we now call the interstellar medium, the thin but pervasive material that fills the spaces between the stars and occasionally gathers into dense clouds that affect the passage of light through the galaxy. His patient accumulation of photographic evidence transformed what had once seemed like mere gaps in the stellar fabric into objects worthy of study in their own right, expanding our understanding of the kinds of structures that populate the space between the stars. Perhaps the most systematic photographic survey of nebulae during this period was conducted by James Edward Keeler at Lick Observatory during the final years of the 19th century. Keeler had previously made important contributions to spectroscopy, including careful measurements of the rotation of Saturn's rings, and when he assumed the directorship of Lick Observatory in 1898, he turned his attention to a comprehensive photographic study of nebulae using the Crossley reflector, a 36-inch telescope that had been donated to the observatory some years earlier but had not yet been put to effective use. Keeler recognized that this instrument, with its wide field of view and light-gathering power, was ideally suited to the photography of faint extended objects, and he set about modifying and improving it for this purpose. The results of Keeler's survey, though cut short by his untimely death in 1900 at the age of 42, were nonetheless remarkable in their implications. Examining his photographic plates, Keeler identified an extraordinary number of faint nebulae that had never been catalogued or even noticed before, ultimately estimating that the portion of the sky he had surveyed contained approximately 120,000 nebulae within reach of his instrument. Even more striking was his observation that the great majority of these nebulae displayed spiral structure when examined carefully, suggesting that spirals were not rare curiosities but rather the most common form of nebula in the universe. Keeler's survey hinted at a cosmos far richer in structure than had previously been imagined, populated by countless spiraling forms whose nature and distance remain to be determined. The technique of using photography to discover new objects through systematic comparison of plates taken at different times was refined by Max Wolf at the observatory in Heidelberg, Germany. Wolf developed and popularized the use of the blink comparator, a device that allowed the observer to view two photographic plates of the same region of sky in rapid alternation, causing any object that had moved or changed between the two exposures to appear to jump back and forth against the stationary background of stars. This technique proved invaluable for the discovery of asteroids and variable stars, and Wolf also applied his photographic methods to the identification of nebulae, ultimately discovering more than 1,500 of these objects over the course of his career. His systematic approach to surveying the sky and his willingness to embrace new technological methods helped to establish photography as an essential tool for the discovery and cataloguing of celestial objects, complementing the visual methods that had served astronomy for centuries. Through the collective efforts of these pioneers and many others whose names are less widely remembered, photography transformed the study of nebulae from a pursuit dependent on the fleeting impressions of individual observers into a discipline based on permanent, objective records that could be examined, measured, and compared over time. The photographic plate became a kind of extended eye, capable of perceiving what no human vision could detect, and the accumulating archive of astronomical photographs provided a foundation for the discoveries and debates that would occupy astronomers in the decades to come. As the 19th century moved toward its final decades, astronomers found themselves in possession of an extraordinary wealth of celestial discoveries, accumulated over more than 100 years of patient observation. Yet this abundance of knowledge had become, in its own way, a kind of gentle burden. The catalogues of nebulae and star clusters had grown considerably since the careful work of Charles Messier, expanding through the tireless sweeps of William Herschel and the southern surveys of his son John, and by the 1880s there existed multiple overlapping lists containing thousands upon thousands of objects, some recorded under different designations in different catalogues, others bearing positions that did not quite agree with one another, and still others that seemed to exist in one compilation but could not be found when observers turned their telescopes to the indicated coordinates. What the astronomical community needed, quite simply, was someone willing to undertake the considerable labor of bringing order to this accumulated knowledge, of weaving together the threads of a century of discovery into a single coherent fabric that might serve observers for generations to come. This task fell to a Danish-born astronomer named John Louis Emil Dreyer, who had made his way from Copenhagen to Ireland as a young man and eventually found his professional home at Armagh Observatory, a venerable institution situated in the gentle countryside of what was then part of the United Kingdom. Dreyer had arrived at Armagh in 1882 to take up the position of director, succeeding Thomas Romney Robinson, who had held that post for a remarkable 59 years. And the observatory itself was a modest establishment compared to the great institutions of the era. Yet it possessed good instruments and, perhaps more importantly, it offered Dreyer the time and institutional support necessary to undertake his great bibliographic project. Armagh Observatory had been founded in 1790, making it one of the older astronomical establishments in the British Isles, and its situation in the north of Ireland provided reasonably dark skies and a tradition of careful positional astronomy that suited Dreyer's methodical temperament perfectly well. The work that would occupy Dreyer through much of the 1880s began with a recognition that William Herschel's general catalogue of nebulae and clusters of stars, published by John Herschel in 1864, had become insufficient for the needs of contemporary observers. That earlier compilation had gathered together 5,079 objects, drawing upon the observations of both Herschel's along with contributions from other astronomers. Yet in the decades since its publication, many new nebulae had been discovered, and many of the older entries required verification or correction of their recorded positions. Dreyer set himself the task of revising and expanding this work, corresponding with observatories across Europe and America to gather the latest discoveries, comparing observations from multiple sources to establish the most reliable coordinates, and noting wherever possible the physical characteristics of each object as described by various observers who had examined them through telescopes of differing apertures and qualities. The result of this sustained effort appeared in 1888 under the title A New General Catalogue of Nebulae and Clusters of Stars, published in the Memoirs of the Royal Astronomical Society, and it contains 7,840 objects arranged in order of their right ascension, which is to say their position measured eastward along the celestial equator from the point where the Sun crosses that circle at the March equinox. Each entry provided the object's coordinates for the epoch of 1860, a description of its appearance, notes on its discoverer and the various catalogues in which it had previously appeared, and such additional information as Dreyer had been able to gather from the astronomical literature. The catalogue employed a system of abbreviations to describe the visual characteristics of each nebula or cluster, indicating whether an object appeared faint or bright, large or small, round or elongated, and whether it contained condensations or central stars, or showed any other notable features that an observer might use to identify it with certainty. The compilation of this catalogue required Dreyer to confront the accumulated errors and duplications that had crept into the astronomical literature over the preceding century, for the early observers had worked without the benefit of precise coordinate systems and had sometimes recorded the same object under different designations when observing it on different nights or when working from imperfect star charts. William Herschel himself, despite his extraordinary skill and dedication, had occasionally logged objects that could not subsequently be verified, either because the original observation had been in error or because the recorded position was insufficiently precise to allow later observers to identify the intended target with certainty. Some entries in the older catalogues proved upon investigation to represent nothing more than small groupings of faint stars that had appeared nebulous in the smaller instruments of an earlier generation, while others turned out to be duplicate observations of objects already catalogued elsewhere in the same compilation. Dreyer worked through these difficulties with characteristic patience, attempting wherever possible to identify the intended object through careful comparison of descriptions and positions, and where such identification proved impossible, he recorded the problematic entries with appropriate notes indicating their uncertain status. The resulting catalogue was not perfect, for some errors inevitably escaped detection and some objects remained ambiguous despite Dreyer's best efforts. Yet it represented an enormous improvement over the scattered and inconsistent compilations that had preceded it, and it quickly became the standard reference work for observers throughout the world. The NGC numbers that Dreyer assigned to each object remain in use to this day, more than a century and a third after their initial publication, and amateur astronomers still speak of NGC 457 or NGC 7789 as readily as their 19th century predecessors might have done. The astronomical community continued to discover new nebulae and clusters, even as Dreyer's new general catalogue was going to press, and within a few years it became apparent that a supplement would be necessary to accommodate these additional objects. Dreyer accordingly prepared the first index catalogue, published in 1895, which added 1,529 new objects to the corpus, and this was followed by a second index catalogue in 1908 containing a further 5,386 entries, bringing the total number of catalogued deep sky objects to well over 13,000. These supplementary catalogues maintain the same format and conventions as the original NGC, and objects listed within them are still identified by their IC numbers, so that a contemporary observer might refer to IC 405, which is a bright nebula in the constellation Auriga, with the same ease as they might mention any NGC object. While Dreyer was engaged in his cataloguing work at Armagh, other astronomers were contributing to the verification and improvement of nebula positions through their own observational programs, and among the most dedicated of these was Guillaume Bigouden at the Paris Observatory, who devoted years of careful work to measuring the precise coordinates of thousands of nebulae using the observatory's equatorial telescopes. Bigouden's observations, carried out over many nights through the 1890s and into the early 20th century, provided independent verification for many of the objects in Dreyer's catalogues and helped to resolve some of the positional uncertainties that had persisted from earlier observations. His work was particularly valuable for the fainter and more difficult objects, where the original discoverers had sometimes recorded only approximate positions, and his published results filled many pages of the annals of the Paris Observatory with long columns of carefully determined coordinates. The classification of nebulae according to their physical characteristics had been a concern of astronomers since the earliest systematic surveys, and William Herschel had proposed one of the first comprehensive schemes for organizing these objects into categories based upon their appearance. In his catalogues and accompanying papers, Herschel distinguished 8 classes of nebulae, ranging from bright nebulae clearly associated with clusters of stars to extremely faint and diffuse patches of luminosity that seemed to possess no stellar component whatsoever. His classification system reflected the observational capabilities of his era, when the distinction between truly nebulous matter and unresolved clusters of distant stars remained uncertain, and when the physical nature of these objects was still a matter of considerable speculation among natural philosophers. John Herschel refined his father's system in his own catalogues, developing a more nuanced scheme of descriptions that allowed observers to characterize nebulae according to their brightness, size, shape, degree of condensation toward the center, and presence or absence of embedded stars. These descriptive conventions were adopted and further systematized by Dreyer in the new general catalogue, which employed a vocabulary of standard abbreviations that remains familiar to observers today. An object might be described as very faint and small and round, or as considerably bright and considerably large and extended in a particular direction, and these descriptions, condensed into brief strings of abbreviations, allowed observers to form an expectation of what they might see before turning their telescopes toward any given entry in the catalogue. Among the categories that emerged from this long process of observation and classification, the planetary nebulae held a particular fascination for observers, despite being relatively rare compared to other types of nebulous objects. William Herschel had coined this term in 1785 to describe a class of nebulae that appeared as small, roughly circular disks of fairly uniform brightness, reminiscent in their appearance of the planets Uranus and Neptune as seen through a telescope. The resemblance was purely superficial. Of course, for planetary nebulae are vastly more distant than any planet in our solar system. Yet the name persisted as a convenient designation for this distinctive class of objects, which we now understand to represent the outer layers of dying stars expelled into space at the end of their nuclear-burning lives. The diffuse nebulae, in contrast to the planetary nebulae, presented observers with irregular and often extensive patches of luminosity, sometimes spanning several degrees of sky and frequently associated with regions of active star formation. The Great Nebula in Orion served as the archetype of this class, its intricate structure of bright and dark regions revealing itself in ever greater detail as telescope apertures increased throughout the 19th century. These objects seemed fundamentally different from the compact planetary nebulae, and astronomers gradually came to recognize that they represented vast clouds of gas and dust illuminated by the hot young stars embedded within them. The spiral nebulae constituted a third major category that emerged from the improving observations of the mid-19th century, initially identified by Lord Rosse through his great reflecting telescope at Birk Castle in Ireland, where the unmistakable spiral structure of objects like Messier 51 became apparent for the first time. These spiral forms seemed to belong to yet another class of celestial object, distinct from both the planetary and the diffuse nebulae, and their true nature as external galaxies comparable to our own Milky Way would not be established until the 1920s, well after Dreyer had completed his cataloguing work. Throughout this period of active classification and cataloguing, a gentle debate persisted within the astronomical community regarding nomenclature, for some observers preferred to retain the familiar Messier numbers for the brighter and more commonly observed objects, while others advocated for the universal adoption of the more comprehensive NGC system. The Messier catalogue had the advantage of priority and familiarity, its objects being among the most prominent and most frequently observed in the night sky, and many astronomers felt an understandable reluctance to abandon designations that had been in continuous use for more than a century. The compromise that emerged, and which persists to this day, allowed both systems to coexist, so that the Great Nebula in Andromeda might be referred to as Messier 31 or as NGC 224, according to the preference of the observer or the conventions of the publication in question. And so, as the 19th century drew toward its close and the 20th century began, astronomers found themselves in possession of a comprehensive and reasonably reliable catalogue of the nebulous objects visible from Earth, organized according to systematic principles and available to observers at every level of expertise. The work of classification and cataloguing would continue, of course, with new discoveries and improved observations requiring constant revision and expansion of the existing compilations. Yet the foundation laid by Dreyer and his predecessors would prove remarkably durable, serving as the basis for deep sky astronomy well into the modern era, and providing a framework within which the true nature of these distant objects would eventually be understood. The question of whether the faint spiral nebulae represented distant congregations of stars, each one a universe unto itself, or whether they were merely luminous clouds of gas and dust residing within our own stellar system, occupied the minds of astronomers and natural philosophers for nearly 2 centuries before any definitive answer could be found. This gentle uncertainty, this patient wondering about the true scale of the cosmos, forms one of the quieter but more profound chapters in the history of our understanding of the night sky, and we may now settle into examining how this question arose, persisted, and was eventually resolved through careful observation and the accumulation of evidence gathered by many hands over many years. The notion that the Milky Way might not be the entirety of creation, that other vast systems of stars might exist at immense distances from our own, first appeared in recognizable form during the middle decades of the 18th century, when natural philosophy was beginning to extend its reach toward the heavens in systematic ways. Thomas Wright of Durham, an English instrument maker and teacher of natural philosophy, published in 1750 a work entitled An Original Theory or New Hypothesis of the Universe, in which he attempted to explain the appearance of the Milky Way as the result of our being situated within a flattened layer of stars. Wright's ideas were somewhat mystical and often difficult to follow, as he was concerned not only with the physical arrangement of the cosmos, but also with theological considerations about the divine order. Yet embedded within his speculations was the suggestion that the faint nebulous patches visible in the night sky might themselves be distant systems of stars, too remote for individual stars to be distinguished, appearing instead as soft glowing regions when viewed through telescopes of the time. 5 years later, in 1755, the German philosopher Immanuel Kant, who would later become renowned for his work in metaphysics and epistemology, published a remarkable cosmological treatise titled Universal Natural History and Theory of the Heavens, in which he developed these ideas with greater clarity and theoretical ambition. Kant had learned of Wright's work through a review published in a Hamburg periodical, and though he perhaps misunderstood some aspects of Wright's original conception, he took the essential idea and extended it considerably. Kant proposed that the Sun and all the visible stars belong to a single vast disk-shaped system, which we perceive as the band of the Milky Way surrounding us, and he further suggested that the elliptical nebulous patches observed by astronomers, those faint smudges of light that neither resolved into stars nor showed the characteristics of cometary material, might be other such systems, other vast congregations of countless stars arranged in similar disk-like formations, located at distances so enormous that even the combined light of millions of suns appeared as nothing more than a dim glow. Kant called these hypothetical external systems island universes, a term that would echo through astronomical discourse for generations, and he imagined the cosmos as containing perhaps an infinite number of such systems, each one a Milky Way in its own right, scattered through the boundless reaches of space. These were bold speculations for their time, and they remained largely speculative throughout the 18th and 19th centuries, as astronomers lacked the means to determine with any certainty whether the spiral nebulae were nearby objects within the Milky Way or distant systems lying far beyond its boundaries. William Herschel, whose systematic surveys of the heavens catalogued thousands of nebulae and clusters, initially believed that all nebulae could eventually be resolved into stars if only sufficiently powerful telescopes were employed. But his later observations led him to accept that some nebulae appeared to be genuinely nebulous, composed of a luminous fluid rather than stars, which complicated the picture considerably. The development of spectroscopy in the 1860s revealed that some nebulae, particularly the diffuse emission nebulae and planetary nebulae, showed bright emission lines characteristic of glowing gas, while others, including many of the spiral nebulae, displayed continuous spectra more consistent with aggregations of stars. Yet even this evidence remained ambiguous, and the question of the spiral nebulae continued to resist definitive resolution as the 19th century gave way to the 20th. By the early decades of the 20th century, the debate had sharpened into a genuine scientific controversy, with capable astronomers taking opposing positions and marshalling observational evidence to support their respective views. On one side stood those who believed the Milky Way to be an enormous system, perhaps the dominant structure of the cosmos, with the spiral nebulae representing relatively nearby objects within or around our own galaxy. On the other side were those who held that the spiral nebulae were indeed island universes, external systems comparable in size and nature to the Milky Way but located at vast distances beyond its boundaries. The evidence available at the time was genuinely ambiguous, and reasonable scientists could interpret the same observations in different ways depending on their assumptions and the weight they gave to various measurements. On the 26th of April, 1920, this controversy was given formal expression in a public discussion held at the Smithsonian Institution in Washington, an event that would later come to be known simply as the Great Debate. The two principal participants were Harlow Shapley, a young and ambitious astronomer from the Mount Wilson Observatory in California, and Heber Curtis, a more senior astronomer from the Lick Observatory. The event was arranged by the National Academy of Sciences as a way of presenting the competing views to a broader audience, and while the actual proceedings were perhaps less dramatic than the name Great Debate might suggest, consisting largely of two prepared lectures followed by discussion rather than any sort of direct confrontation, the occasion has come to symbolize the moment when the question of the spiral nebulae reached its point of maximum uncertainty before eventual resolution. Harlow Shapley came to the debate with a particular view of the Milky Way that he had developed through his studies of globular clusters, those dense spherical collections of hundreds of thousands of stars that orbit around the center of our galaxy. Using observations of variable stars within these clusters, Shapley had constructed a model of the Milky Way that was far larger than previous estimates had suggested, with a diameter of perhaps 300,000 light-years, making it an enormous structure that seemed to dominate the cosmos. In Shapley's view, a galaxy of such tremendous size left little need for external island universes, and the spiral nebulae could be accommodated as relatively minor features within or near the Milky Way itself. He pointed to various lines of evidence supporting this interpretation, including measurements made by his colleague Adrian van Maanen at Mount Wilson, who claimed to have detected rotation in several spiral nebulae by comparing photographic plates taken years apart. If van Maanen's measurements were correct, and the spiral nebulae were rotating at detectable rates over spans of just a few years, then simple geometry required that these objects must be relatively nearby, for if they were truly at distances of millions of light-years, as the island universe theory required, then the observed rotation would imply linear velocities far exceeding the speed of light, which was physically impossible. Van Maanen was a careful and respected observer, and his measurements seemed to provide strong evidence against the island universe hypothesis, though subsequent investigations would reveal that his results were in error, likely due to subtle systematic effects in his measurement techniques. Heber Curtis, for his part, defended the island universe theory with equal conviction and his own array of supporting evidence. Curtis argued for a considerably smaller Milky Way, perhaps 30,000 light-years in diameter, which made the idea of external systems of comparable size more plausible. He had studied the spiral nebulae extensively, particularly the Great Spiral in Andromeda, and he had noticed several features that suggested these objects were distant stellar systems rather than nearby gas clouds. Curtis had observed novae, those temporary stellar outbursts that appear as new stars in the sky before fading away, within the spiral nebulae, and he noted that these novae were consistently much fainter than the novae that appeared within the Milky Way. If the spiral novae were similar in intrinsic brightness to galactic novae, then their faintness implied enormous distances, placing the spiral nebulae far beyond the boundaries of our own system. Curtis also noted the dark lanes visible in some edge-on spiral nebulae, which resembled the obscuring dust clouds known to exist within our own galaxy, and the overall structural similarity of the spirals to the Milky Way as we might imagine it appearing from outside. The case was complicated. However, by one particularly puzzling observation that had occurred decades earlier. In 1885, a new star had appeared in the Great Andromeda Nebula, an object that came to be designated S Andromedae. This new star had grown remarkably bright, reaching approximately 6th magnitude at its peak, which meant it was nearly visible to the naked eye and appeared to rival or even exceed the combined luminosity of the entire nebula in which it appeared. If the Andromeda Nebula was indeed a distant island universe containing billions of stars, how could a single star possibly outshine all the rest combined? This single observation seemed to argue strongly against the island universe interpretation, for it implied either that S Andromedae was impossibly luminous or that the Andromeda Nebula must be relatively nearby and therefore much smaller than the island universe theory required. What astronomers of that era did not yet understand was that S Andromedae was not an ordinary nova at all, but rather what we now call a supernova, a catastrophic stellar explosion of a type far more luminous than any ordinary nova, capable of briefly outshining an entire galaxy. The confusion caused by this single event, the failure to recognize that there existed two fundamentally different types of stellar outbursts with vastly different intrinsic luminosities, would persist for several more decades and contributed significantly to the uncertainty surrounding the Great Debate. Both Shapley and Curtis, as it would turn out, were partially correct and partially mistaken in their arguments and conclusions. Shapley was right that the Milky Way was considerably larger than earlier estimates had suggested, though his figure of 300,000 light-years was itself an overestimate, inflated by errors in his distance calibrations that resulted from a failure to account fully for interstellar absorption, the dimming of starlight by dust in the plane of the galaxy. Curtis was correct that the spiral nebulae were indeed external systems at vast distances, but his smaller estimate for the size of the Milky Way was itself too conservative. The measurements that Van Manen had presented, which seemed to provide such strong evidence against the island universe hypothesis, were simply wrong, the result of systematic errors that were not recognized at the time. The true resolution of the debate would require better distance measurements and a clearer understanding of the different types of variable stars and stellar explosions. The key to unlocking these cosmic distances lay in the work of Henrietta Swan Leavitt, a human computer employed at the Harvard College Observatory, who in 1912 published her discovery of a remarkable relationship between the periods and luminosities of a type of variable star known as Cepheid variables. Leavitt had been studying variable stars in the Magellanic Clouds, those two satellite galaxies visible from the southern hemisphere, and she noticed that the brighter Cepheids had longer periods of variation, while the fainter ones had shorter periods. Because all the Cepheids in each Magellanic Cloud were at essentially the same distance from Earth, Leavitt could determine their relative luminosities directly from their apparent brightnesses, and she found that a simple mathematical relationship connected period and luminosity. This period-luminosity relationship meant that by measuring how long a Cepheid variable took to go through its cycle of brightening and dimming, one could determine its intrinsic luminosity, and by comparing that intrinsic luminosity to its observed apparent brightness, one could calculate its distance. The Cepheid variables became, in effect, standard candles, cosmic yardsticks that could be used to measure distances far beyond the reach of traditional parallax methods. The application of Leavitt's period-luminosity relationship to the question of the spiral nebulae would eventually provide the definitive evidence needed to resolve the Great Debate, though this would not occur until 1924, when Edwin Hubble succeeded in identifying individual Cepheid variables in the Andromeda Nebula and used their periods and apparent brightnesses to calculate a distance of approximately 900,000 light-years, placing Andromeda far beyond the boundaries of even Shapley's enlarged Milky Way. This measurement, though later revised to an even greater distance, established beyond reasonable doubt that the spiral nebulae were indeed island universes, external galaxies comparable to our own, and that the cosmos was vastly larger and more populous than the single galaxy universe that Shapley had imagined. And so the question that had been posed in various forms since the time of Kant and Wright, the gentle wondering about whether we inhabit a singular island of stars in an otherwise empty void, or whether our Milky Way is but one of countless such islands scattered through the immensity of space, was finally answered through the patient accumulation of evidence over nearly 2 centuries, each generation of astronomers contributing some small piece to the puzzle, until at last the picture became clear and we understood our true place within a cosmos of galaxies beyond counting, stretching outward in all directions to distances that the human mind can barely comprehend. On the evening of October the 6th, 1923, a quiet revolution began on a mountain in Southern California, though no one present could have known it at the time. Edwin Hubble, a tall and rather formal man who had once been a Rhodes Scholar and a high school basketball coach before finding his way to the stars, was working at the 100-inch Hooker telescope at Mount Wilson Observatory, and on this particular night he turned the great instrument toward the familiar spiral nebula in the constellation Andromeda, catalogued as Messier 31, that same soft glow that had puzzled astronomers for centuries. The Hooker telescope was then the largest in the world, its mirror spanning more than 2.5 meters across, and it gathered light from the depths of space with a patience and precision that smaller instruments could not match. Hubble exposed a photographic plate to the faint light of the outer regions of the Andromeda spiral, and when he later examined that plate, he noticed something that would change our understanding of the universe in ways both profound and permanent. What Hubble saw, at first, appeared to be a nova, one of those stars that suddenly flares bright and then fades away, and he marked the position on his plate with the notation that astronomers commonly used. He wrote the letters VAR followed by an exclamation point, indicating that he had found a variable star of some kind, and this initial marking would later become one of the most famous notations in the history of astronomy, though at the moment it was simply a working observation made in the ordinary course of a night's work. But as Hubble examined the plate more carefully, and as he compared it with earlier photographs of the same region taken on different nights, he reconsidered his identification. Perhaps, he thought, this was not a variable star at all, but rather a nova, a stellar explosion of the type that had been observed in nebulae before, and so he crossed out his original notation and replaced it with the letter N, the standard abbreviation for nova. The plate itself, with its crossings out and corrections, would survive to become a treasured artifact, a record of a mind working through uncertainty toward clarity. Yet the story did not end with that correction, for as Hubble continued his observations over the following weeks and months, comparing new plates with old ones in the patient manner that astronomical research requires, he began to see something remarkable. The star he had marked was not behaving like a nova at all. Novae flare suddenly and then decline, but this star was doing something different, something rhythmic and repeating. It was brightening and dimming in a regular pattern, a slow pulse of light that followed a predictable cycle, and Hubble recognized this behavior as the signature of a very particular type of star. This was a Cepheid variable, one of those cosmic beacons that Henrietta Leavitt had studied years before in the Magellanic Clouds, and the realization must have been extraordinary even for a man of Hubble's measured temperament. For if this was truly a Cepheid, then its distance could be calculated using the period luminosity relationship that Leavitt had discovered, and if that distance could be calculated, then the great question of the spiral nebulae might finally be answered. The star that Hubble had found would eventually be designated V1, the first confirmed variable star in Messier 31, and it remains a landmark object to this day, still pulsing with the same steady rhythm that Hubble detected nearly a century ago. By measuring the period of its variation, which turned out to be approximately 31.5 days, and by applying Leavitt's relationship between period and true brightness, Hubble could work out how luminous this star actually was. And by comparing that true brightness with how faint it appeared in his photographs, he could determine how far away it must be for its light to have dimmed to such a degree. The mathematics was straightforward once the principle was understood, and when Hubble completed his calculations, the number he arrived at was staggering. The Andromeda Nebula, he concluded, lay at a distance of approximately 900,000 light-years from our own position in space. Now, this figure was not perfectly accurate, as we now know that the true distance to the Andromeda Galaxy is closer to 2.5 million light-years, a discrepancy that arose from various calibration errors that would only be corrected in later decades. But even Hubble's underestimate was sufficient to prove the essential point. 900,000 light-years was vastly greater than any reasonable estimate of the size of the Milky Way. If the Andromeda spiral was truly that distant, then it could not possibly be a cloud of gas within our own stellar system. It had to be something else entirely, a separate congregation of stars lying far beyond the boundaries of our galaxy, an island universe in its own right, comparable in scale and grandeur to the Milky Way itself. The island universe theory, which had been debated and doubted for so many years, was now supported by direct measurement, and the universe had suddenly become immeasurably larger. Hubble continued his observations throughout 1924, identifying additional Cepheid variables in Messier 31 and in other spiral nebulae as well, building a body of evidence that grew more compelling with each new plate he exposed and examined. He was a careful worker, methodical in his approach, and he did not rush to announce his findings until he felt confident that they would withstand scrutiny. In preparing to present his results to the wider astronomical community, he chose the annual meeting of the American Astronomical Society, which was to be held in Washington, D.C., beginning on the first day of January, 1925. This was a prestigious venue, attended by the leading astronomers of the day, and Hubble's paper was scheduled to be read as part of a joint session with the American Association for the Advancement of Science. As it happened, Hubble himself did not attend the meeting. The reasons for his absence are not entirely clear from the historical record, though it may simply have been a matter of the long journey from California to the East Coast being impractical at that time of year. In any case, the task of presenting Hubble's findings fell to Henry Norris Russell, the distinguished Princeton astronomer who had himself contributed so much to our understanding of stellar evolution, and Russell read the paper to the assembled scientists on Hubble's behalf. The presentation was received with great interest and was quickly recognized as a landmark contribution, though the moment passed without fanfare or ceremony. The universe had been transformed, and yet the day continued much as any other day might, with papers being read and questions being asked and astronomers making notes in their little books. In the years that followed, Hubble turned his attention to the broader question of how these newly confirmed galaxies might be organized and classified, for it had become clear that the universe contained an enormous variety of these distant stellar systems, each with its own shape and structure and character. Working at Mount Wilson with the great telescope that had served him so well, he developed a classification scheme that would provide a framework for understanding this diversity, a system that remains in use, with modifications, to the present day. This scheme, which Hubble published in 1926, divided galaxies into several broad categories based on their visual appearance, and it brought a kind of order to what had previously seemed a bewildering profusion of forms. The first category in Hubble's system was the elliptical galaxies, those smooth and featureless collections of stars that appear as simple ovals or circles when viewed through a telescope. Hubble designated these with the letter E followed by a number ranging from 0 to 7, where E0 indicated a galaxy that appeared perfectly circular and E7 indicated one that was highly elongated, almost cigar-shaped when seen from our particular vantage point. These elliptical systems showed little internal structure, no spiral arms or dust lanes or bright regions of star formation, just the soft and even glow of billions of stars blending together into a diffuse luminosity. The second major category was the spiral galaxies, those magnificent pinwheel structures that had so captivated observers since Lord Rosse first glimpsed them through his great telescope at Birr Castle. Hubble divided these into subcategories labeled SA, SB, and SC, based on how tightly wound their spiral arms appeared and how prominent their central bulge was relative to their disk. An SA galaxy had tightly wound arms and a large central bulge, while an SC galaxy had loosely wound arms and a smaller bulge, with SB representing an intermediate form. Within this scheme, there was also room for the barred spirals, those galaxies in which the spiral arms appear to emerge not from the central bulge directly, but from the ends of a straight bar of stars that passes through the center, and these were designated with the letters SB followed by the same lowercase letters indicating how tightly wound they were. Finally, there were the irregular galaxies, those systems that did not fit neatly into either the elliptical or spiral categories, lacking the smooth symmetry of the former or the organized structure of the latter. The Magellanic Clouds, those companion galaxies to our own Milky Way, were examples of this type, and Hubble acknowledged that not every galaxy in the universe would conform to a tidy scheme. Nature, after all, is under no obligation to organize itself for our convenience, and a good classification system must have room for exceptions and variations and all the beautiful messiness of reality. Throughout this period of discovery and classification, Hubble was assisted by a remarkable man named Milton Lassell Humason, who had come to astronomy by one of the most unusual paths imaginable. Humason had begun his working life as a mule driver on Mount Wilson, hauling supplies up the steep trails to the observatory during its construction, and he had no formal education beyond the 8th grade. But he possessed a natural aptitude for the technical work of astronomy, a steady hand and a patient eye, and he gradually worked his way up from janitor to night assistant to full-fledged observer. His skill in obtaining spectrograms of faint and distant objects was unmatched, and the measurements he made were essential to the discoveries that Hubble would announce to the world. It was a collaboration between two very different men, one with degrees from the finest universities and one who had never attended high school, united by their shared dedication to understanding the heavens. The culmination of this collaboration came in 1929, when Hubble published a paper that would prove even more consequential than his earlier work on the distances to the spiral nebulae. By combining his own distance measurements with the radial velocity measurements that had been accumulating over the years, including those made by Vesto Slipher and those obtained by Humason at Mount Wilson, Hubble noticed a striking pattern. The more distant a galaxy was, the faster it appeared to be receding from us. Its light shifted toward the red end of the spectrum by an amount that was proportional to its distance. This relationship, which came to be known as Hubble's law, suggested something almost unimaginable, that the universe itself was expanding, that the space between galaxies was stretching like the surface of a balloon being inflated, carrying the galaxies apart from one another in a vast and stately recession. The implications of this discovery were profound in ways that extended far beyond the boundaries of astronomy, touching on questions of philosophy and cosmology and the ultimate nature of existence. If the universe was expanding now, then it must have been smaller in the past, and if one traced that expansion backward in time, one arrived eventually at a moment when all the matter and energy in the cosmos was concentrated in a single point of unimaginable density. This was the seed of what would later be called the Big Bang Theory, though Hubble himself was always cautious about the theoretical implications of his observations, preferring to let the data speak for itself while others drew the larger conclusions. He had measured, and he had found a pattern, and that was enough for one lifetime of work. As the 20th century progressed and astronomers refined both their instruments and their understanding of the physical processes at work in the universe, it became gradually apparent that the word nebula, which had served for so long as a convenient label for anything fuzzy and extended in the heavens, was actually concealing a remarkable diversity of celestial objects. What had once seemed a relatively uniform category of cosmic clouds was slowly revealed to comprise several quite distinct types of phenomena, each with its own physical nature, its own characteristic appearance, and its own place in the grand cycles of stellar birth, life, and death. By the year 1930, a reasonably complete taxonomy of these cosmic clouds had emerged, and astronomers could speak with some confidence about the different kinds of nebulae that populated the galaxy, distinguishing between them on the basis of how they produced their light, what materials they contained, and how they had come into being. This gradual process of classification, which unfolded over several decades through the patient work of many observers and theorists, represents one of the quieter but deeply satisfying achievements of early 20th century astronomy, and we shall now trace its outlines in the gentle manner appropriate to such a restful subject. Among the most visually striking of all nebulae are those that glow with their own characteristic light, the objects that astronomers came to call emission nebulae, and within this category the most significant are the vast clouds known as H2 regions, so named because they consist primarily of ionized hydrogen, which is designated by the chemical symbol H with a Roman numeral 2 indicating that the hydrogen atoms have lost their electrons. The physical understanding of how these great glowing clouds produce their light was considerably advanced by the work of Edwin Hubble, who published an important study in 1922 examining the relationship between nebulae and the stars that appeared to be associated with them. Hubble observed that the brightest emission nebulae were invariably found in close proximity to extremely hot stars, the blue and white giants whose surface temperatures could reach 30,000 degrees or more, and he demonstrated that the luminosity of a nebula was directly related to the brightness and temperature of its associated star. This correlation strongly suggested that the nebulae were not generating their light independently, but were instead responding in some way to the intense radiation being poured into them by their neighboring stars. The physical mechanism behind this emission was understood through the developing science of atomic physics, which had been revolutionized in the preceding decades by the work of Niels Bohr and others, who had elucidated the structure of atoms and the behavior of electrons within them. When ultraviolet radiation from a very hot star strikes a hydrogen atom in the surrounding gas cloud, the energy of the photon is sufficient to knock the electron completely free from the atomic nucleus, a process called ionization. The freed electron then wanders through the nebula until it eventually encounters another hydrogen nucleus and is captured back into an atomic orbit, a process called recombination. As the electron settles back into progressively lower energy states within the atom, it releases photons of very specific wavelengths corresponding to the energy differences between these quantum levels, and it is this emission of light during recombination that causes the nebula to glow. The characteristic reddish-pink color of many emission nebulae is produced primarily by photons emitted when electrons drop into a particular energy level of hydrogen, producing what is known as hydrogen alpha radiation at a wavelength of 6,563 angstroms. The spectra of these objects therefore show bright emission lines rather than the continuous rainbow of colors that one would see from a solid glowing body. And this spectroscopic signature became one of the primary means by which emission nebulae could be identified and distinguished from other types. Quite different in nature are the reflection nebulae, which do not generate their own light through any process of ionization or atomic emission, but instead shine by reflecting and scattering the light of nearby stars. Much as a cloud of fine dust motes in a sunbeam will become visible by scattering the sunlight that falls upon it. The key evidence for this interpretation came from the spectroscopic work of Vesto Melvin Slipher, an astronomer working at the Lowell Observatory in Arizona, who in 1912 published the results of his careful examination of the nebulosity surrounding the stars of the Pleiades, that lovely open cluster in the constellation Taurus that has been admired by humanity since ancient times. When Slipher obtained spectra of the faint blue haze that envelops these stars, he discovered something quite unexpected and revealing. The spectrum of the nebulosity was not the emission line spectrum characteristic of a glowing gas, but was instead essentially identical to the absorption line spectrum of the stars themselves. This could only mean that the light from the nebula was not being generated within the nebula material, but was instead starlight that had been redirected toward the observer after bouncing off particles within the cloud. Subsequent work confirmed and extended Slipher's interpretation, revealing that reflection nebulae typically appear blue in color because the small dust particles that compose them scatter shorter wavelengths of light more efficiently than longer wavelengths. The same physical phenomenon that makes the daytime sky appear blue when sunlight scatters off molecules in the atmosphere. Unlike emission nebulae, which require the presence of extremely hot stars capable of producing ionizing ultraviolet radiation, reflection nebulae can be illuminated by cooler stars whose radiation is insufficient to ionize the surrounding gas but is quite capable of being reflected by dust grains. The presence of a reflection nebula, therefore, tells astronomers something about the local environment, indicating that dust is present in the vicinity of a star but that the stellar temperature is not high enough, or the dust is not close enough to the star, for ionization to occur. In many regions of space, emission and reflection nebulae coexist in complex arrangements, with the hottest stars ionizing the gas in their immediate vicinity to produce glowing emission regions, while cooler stars nearby merely illuminate the dust to create bluish reflection nebulae. And the interplay between these different zones creates some of the most beautiful and intricate structures visible in astronomical photographs. A quite distinct category of nebula object, one that had puzzled astronomers since the 18th century, comprises the planetary nebulae, those small, often roughly circular or ring-shaped objects that William Herschel had named for their superficial resemblance to the disks of planets as seen through a telescope. The crucial insight into the nature of these objects came in 1864, when the English amateur astronomer William Huggins turned his spectroscope upon the planetary nebula known as the Cat's Eye Nebula in the constellation Draco and obtained a spectrum that was utterly unlike anything produced by a collection of stars. Instead of the continuous spectrum crossed by dark absorption lines that Huggins had come to expect from stellar objects, the planetary nebula showed only a few bright emission lines against an otherwise dark background, demonstrating unambiguously that these objects were composed of luminous gas rather than aggregations of unresolved stars. This spectroscopic proof of gaseous nature was a landmark in the understanding of nebulae, providing the first definitive evidence that at least some of the cloudy objects scattered across the sky were genuinely diffuse masses of glowing matter rather than distant star systems. As the 20th century progressed and astronomers developed a clearer understanding of stellar evolution, the true nature of planetary nebulae gradually became apparent. These objects, it was realized, represent a particular phase in the death of certain types of stars, specifically those of roughly the same mass as our Sun or somewhat larger, which end their lives not in violent explosions but in a gentler process of expansion and mass loss. When such a star exhausts the nuclear fuel in its core, it swells into a red giant and eventually ejects its outer layers into space, creating an expanding shell of gas that is illuminated and ionized by the hot, exposed core of the dying star. The roughly spherical or ring-like appearance of many planetary nebulae is a consequence of this ejection process, with the glowing shell representing the material that was once the outer atmosphere of a star that is now transforming into a small, dense remnant known as a white dwarf. The understanding that planetary nebulae represent dying stars returning their processed material to the interstellar medium connected these objects to the broader cycles of stellar birth and death that were gradually being recognized as fundamental to the evolution of galaxies. Perhaps the most enigmatic of all the nebula categories are the dark nebulae, those regions of apparent emptiness scattered across the luminous band of the Milky Way that had puzzled observers since William Herschel first noted them in the late 18th century. The question of whether these dark patches represented actual holes or gaps in the stellar distribution, genuine regions where stars were simply absent, or whether they were instead foreground clouds of obscuring material that blocked the light of more distant stars, remained contentious well into the 20th century. The definitive case for the obscuring cloud interpretation was built largely through the meticulous observational work of Edward Emerson Barnard, an American astronomer who devoted decades of his career to the careful photography and study of these dark markings. In 1919, Barnard published his catalogue of 182 dark nebulae, providing detailed positions, descriptions, and photographs of these objects and arguing persuasively that they represented dense clouds of absorbing matter rather than voids in the stellar fabric. The evidence that Barnard and others assembled was compelling in its cumulative weight. The dark nebulae often showed sharply defined edges and complex, irregular shapes that would be difficult to explain if they were simply regions where stars happened not to exist, whereas such boundaries made perfect sense if the darkness was caused by an intervening cloud with a definite spatial extent. Many dark nebulae appeared to be physically connected to bright nebulae, suggesting that they were composed of the same material but simply lacked illuminating stars in their immediate vicinity. Statistical studies of star counts in and around dark nebulae showed exactly the pattern one would expect from obscuration, with the number of visible stars dropping sharply within the dark regions and recovering to normal levels beyond their boundaries. By the 1920s, the interpretation of dark nebulae as clouds of dust and gas that absorb and scatter the light of background stars had become the accepted view, and astronomers began to realize that such obscuring material was far more widespread in the galaxy than had previously been appreciated, affecting observations of distant objects even in regions that did not appear obviously dark to the eye. One final category of nebula deserves mention in our gentle survey, and that is the supernova remnant, the expanding shell of debris left behind when a massive star ends its life in a catastrophic explosion. The most famous and best-studied example of this class is the Crab Nebula in the constellation Taurus, a chaotic, filamentary mass of glowing gas that had been observed and catalogued since the 18th century, but whose true significance was not appreciated until the 1920s. In that decade, several astronomers, including the Swedish astronomer Knut Lundmark, drew attention to a remarkable historical connection. The position of the Crab Nebula in the sky corresponded almost exactly to the location of a brilliant guest star that had been recorded by Chinese and other astronomers in the year 1054 of the Common Era, a star so bright that it had been visible in daylight for several weeks before slowly fading from view. The inference was that the Crab Nebula represented the still expanding remains of the star that had exploded nearly 9 centuries earlier, the debris cloud of what we would now call a supernova. This connection between a present-day nebula and a historical stellar explosion opened up an entirely new way of thinking about certain nebular objects, linking them to the most violent events in the stellar life cycle and providing astronomers with nearby laboratories for studying the aftermath of these cosmic catastrophes. It should be noted, in the interest of completeness, that not all categories of nebulae were recognized by 1930. Protoplanetary nebulae, which represent a brief transitional phase in the evolution of dying stars between the red giant stage and the planetary nebula stage, were not identified as a distinct class until much later in the 20th century, when improved infrared observations revealed their characteristic properties. The taxonomy of nebulae, like all scientific classifications, continued to evolve and refine itself as new observations and theoretical insights accumulated. But by 1930, the major categories that we have described were reasonably well established, and astronomers possessed a coherent framework for understanding the diverse array of cosmic clouds that their telescopes revealed. The recognition that a single word, nebula, actually encompassed such different phenomena, from the birth clouds of new stars to the death shrouds of old ones, from dense obscuring dust to tenuous glowing gas, represented a significant deepening of astronomical understanding and prepared the way for the more detailed investigations that would follow in subsequent decades. And so we come now to the places themselves, the observatories where this slow and patient work was carried out, the buildings and domes and instruments that made possible the careful study of those faint luminous patches scattered across the night sky. For it is one thing to wonder about the nebulae, to speculate on their nature and distance and composition, but it is quite another to gather the light they send us across such unimaginable distances, to capture that light and spread it into its component colors, to record it on glass plates that might be measured and compared and studied at leisure in the quiet hours of the following day. The story of nebula research is therefore also a story of infrastructure, of the steady accumulation of better instruments housed in better locations, funded by individuals and institutions who understood that the universe would only reveal its secrets to those who built the tools capable of asking the right questions in the right way. In the United States, the latter half of the 19th century saw a remarkable flowering of astronomical ambition, driven in large part by the private fortunes of individuals who wished to leave some lasting mark upon the advancement of human knowledge. Among these benefactors was James Lick, a Pennsylvania-born piano maker and land speculator who had accumulated considerable wealth in California during the years following the gold rush, and who determined that his fortune should be devoted to the construction of a great telescope, one that would surpass any then in existence. Lick died in 1876, but his bequest of $700,000 made possible the creation of the observatory that would bear his name, perched atop Mount Hamilton in the Diablo Range east of San Jose, at an elevation of some 4,000 feet above the sea. The Lick Observatory received its first light in 1888, and at its heart was a magnificent 36-inch refracting telescope, which is to say a telescope that gathered and focused light using a large glass lens rather than a curved mirror. This great refractor, with its lens crafted by the firm of Alvan Clark and Sons, was for a time the largest refracting telescope in the world, and its placement at such altitude, above much of the turbulent air of the lower atmosphere, meant that astronomers could observe under conditions of unusual steadiness and clarity. The mountain air was thin and cold, the nights were dark, and the stars and nebulae held still in the eyepiece in a way that observers at sea-level observatories could only envy. At Lick, the astronomer James Keeler would later use the Crossley reflector, a 36-inch reflecting telescope donated to the observatory in 1895, to photograph nebulae with a sensitivity and resolution that revealed spiral structure in objects previously thought to be formless clouds. Keeler's photographs, taken in the closing years of the 19th century and the opening years of the 20th, demonstrated that spiral nebulae were far more numerous than anyone had suspected, and that their delicate arms and whorls could be captured on photographic plates with exposures lasting many hours through the cold mountain nights. Meanwhile, in Southern California, another figure was at work whose ambition and persuasive abilities would reshape the landscape of American astronomy. George Ellery Hale was a solar physicist of considerable talent, but his greatest gift may have been his capacity to envision large projects and to convince wealthy individuals to fund them. Hale understood that the future of astronomy lay in ever larger telescopes placed at ever better sites, and he devoted much of his career to making such instruments a reality. In 1904, Hale established the Mount Wilson Observatory in the San Gabriel Mountains above Pasadena, at an elevation of some 5,700 feet, where the seeing conditions were exceptionally fine and the skies were as yet largely free from the artificial lights of the growing city below. The first major instrument at Mount Wilson was a 60-inch reflecting telescope, completed in 1908, which used a large curved mirror to gather and focus light. This telescope was for a time the largest in the world, and it enabled detailed spectroscopic studies of stars and nebulae alike. But Hale was not content with 60 inches. With funding from John D. Hooker, a Los Angeles businessman, Hale oversaw the construction of an even larger instrument, the 100-inch Hooker telescope, which saw first light in November of 1917. The mirror for this telescope, a disc of glass 100 inches in diameter, had been cast at the Saint-Gobain glassworks in France and shipped across the Atlantic and then overland to California, where it was ground and polished and figured with extraordinary care. The Hooker telescope was a triumph of engineering and patience, and for nearly 3 decades it remained the largest telescope in the world, the instrument with which Edwin Hubble would eventually demonstrate that the spiral nebulae were in fact distant galaxies far beyond the boundaries of our own Milky Way. On the eastern seaboard of the United States, the Harvard College Observatory pursued a rather different approach to the study of the heavens, one that emphasized systematic survey work and the careful classification of stellar spectra. Under the direction of Edward Charles Pickering, who served as director from 1877 until 1919, the Harvard Observatory undertook an ambitious program of photographic sky surveys, exposing glass plates night after night and accumulating an archive of hundreds of thousands of stellar spectra that could be examined and catalogued at leisure. The work of examining these plates and classifying the spectra they contained was carried out in large part by a group of women who came to be known as the Harvard Computers, though the term does little justice to the skill and insight they brought to their labors. Among them was Williamina Fleming, who had been born in Dundee, Scotland, and who had come to work at the observatory initially as a maid in Pickering's household before being recruited to assist with the plate examination. Fleming developed a system for classifying stellar spectra based on the strength of certain absorption lines, and she discovered numerous stars with unusual spectra, as well as the Horsehead Nebula in Orion, which she identified on a photographic plate in 1888. Annie Jump Cannon joined the Harvard Observatory in 1896 and devoted her career to the classification of stellar spectra, refining and extending the work of Fleming and others to create the system of spectral classification O, B, A, F, G, K, M that remains in use to this day. Cannon personally classified the spectra of several 100,000 stars over the course of her career, working with a speed and accuracy that astonished her colleagues. Henrietta Swan Leavitt, another of the Harvard computers, made a discovery that would prove essential to the measurement of cosmic distances. While examining photographic plates of the Magellanic Clouds, those two luminous patches visible in the southern sky, Leavitt identified a class of variable stars known as Cepheids, and she noticed that the brighter Cepheids had longer periods of variation. This relationship between period and luminosity, published in 1908 and refined in 1912, meant that by measuring the period of a Cepheid's variation, one could determine its intrinsic brightness, and by comparing that intrinsic brightness to its apparent brightness in the sky, one could calculate how far away it must be. This period luminosity relation would later enable Hubble to estimate the distances to the spiral nebulae and to demonstrate their extragalactic nature. Across the Atlantic, European astronomers were also constructing observatories and developing instruments suited to the study of nebulae, though the pattern of funding and organization differed considerably from that which prevailed in America. In Britain, much astronomical work was carried out by private individuals of independent means, gentlemen astronomers who built their own observatories and pursued their own research programs without the support of universities or government institutions. One such figure was Isaac Roberts, a Welsh engineer and businessman who had made his fortune in the building trade and who devoted his later years to the photographic study of nebulae and star clusters. In 1886, Roberts established a private observatory at Crowborough in Sussex, where he installed a 20-inch reflecting telescope of his own design, equipped for long-exposure photography. Roberts developed techniques for guiding the telescope during exposures lasting many hours, compensating for the rotation of the Earth so that the stars remained fixed upon the photographic plate. His photographs of the Andromeda Nebula, taken in the late 1880s, revealed for the first time the spiral structure of that great object, with its bright central condensation and its delicate arms trailing outward into the surrounding darkness. Roberts believed, incorrectly as it turned out, that he was observing a solar system in the process of formation, but his photographs nonetheless represented a significant advance in the imaging of nebulae. In Germany, the Heidelberg Königstuhl Observatory, established on the Königstuhl Hill above Heidelberg, developed an active program of astrophotography in the closing years of the 19th century and the opening decades of the 20th. Max Wolf, who became director of the observatory in 1893, was a pioneer in the use of photography to discover asteroids and to study the structure of the Milky Way and the forms of nebulae. Wolf's wide-field photographs revealed the presence of dark nebulae, regions of the sky where obscuring clouds of dust blocked the light of more distant stars, and he catalogued many of these dark markings. The Königstuhl Observatory also participated in international efforts to create photographic atlases of the entire sky, contributing plates that would be measured and analyzed for decades to come. Back in the United States, the Lowell Observatory was founded in 1894 by Percival Lowell, a wealthy Bostonian who had become fascinated by the possibility of intelligent life on Mars and who established his observatory in Flagstaff, Arizona, in part to study that planet under the clear skies of the high desert. Though Lowell's Martian enthusiasms have not aged well, his observatory made genuine contributions to the study of nebulae, particularly through spectroscopic observations that helped to determine the chemical composition and physical conditions within these objects. Vesto Slipher, working at Lowell Observatory in the years before the First World War, measured the radial velocities of numerous spiral nebulae by examining the Doppler shifts in their spectra, and he found that many of them were receding from us at remarkably high speeds, a discovery that would later contribute to the recognition that the universe itself was expanding. Throughout this period, the instruments used to study nebulae were steadily improving. Spectrographs, the devices used to spread starlight into its component wavelengths so that absorption and emission lines could be identified and measured, became more efficient and more compact, allowing fainter objects to be studied in less time. The design of prisms and diffraction gratings was refined, and astronomers developed techniques for calibrating their spectra against laboratory standards so that wavelengths could be measured with increasing precision. Photographic emulsions also improved considerably over these decades. The wet collodion plates of the mid-19th century gave way to dry gelatin plates that were more sensitive and far more convenient to use, and these in turn were superseded by emulsions of ever greater sensitivity to blue and violet light. Special emulsions sensitive to red and infrared wavelengths were developed, allowing astronomers to photograph objects and features that would otherwise have remained invisible. The hypersensitization of plates, treating them with various chemicals or gases to increase their responsiveness to faint light, became a standard technique at major observatories. It is worth pausing to note the different patterns of funding that supported astronomical research in America and Europe during this period. In the United States, the great observatories of the late 19th and early 20th centuries were built almost entirely with private money, the bequests and donations of wealthy individuals who saw in astronomy a worthy object for their philanthropy. James Lick, John D. Hooker, Andrew Carnegie, and others provided the funds that built the telescopes and observatories that would transform our understanding of the universe. American universities and the federal government played relatively little role in funding astronomical research during this era. In Europe, by contrast, astronomical observatories were more often supported by universities and by national governments, following a tradition that stretched back centuries to the royal observatories of Paris and Greenwich. This difference in funding had various consequences for the nature of the research that was carried out, with American observatories tending toward large telescopes and ambitious observational programs, while European institutions often emphasized theoretical work and the careful analysis of existing data. And so, as the 20th century progressed, the infrastructure of nebular research grew ever more capable, with larger telescopes at higher and darker sites, better spectrographs, and more sensitive photographic plates, and a growing community of astronomers, both men and women, devoted to the patient work of observation and analysis. The nebulae, those faint luminous patches that had puzzled observers for so long, were gradually giving up their secrets, and the outlines of a new understanding of the universe, vaster and stranger than anyone had imagined, were slowly beginning to emerge.